If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The solar system, a cosmic neighborhood. Imagine standing on a cliff at the edge of existence, gazing into the vastness of space, a silent realm of infinite possibilities. Somewhere in that unfathomable expanse lies our cosmic home, the solar system. A delicate balance of celestial bodies bound by invisible forces. It is not just our neighborhood, but a time capsule holding the secrets of how worlds are born and shaped. But what exactly defines the solar system? Where does it begin and end? To truly understand it, we must embark on a journey that takes us from the fiery heart of the sun to the icy outskirts where comets sleep in solitude. The solar system is more than just a collection of planets and moons. It is a complex dance orchestrated by gravity, with the sun as its enduring conductor. Born approximately 4.6 billion years ago from a swirling cloud of gas and dust, this celestial ballet has been ongoing ever since. The sun's gravitational pull serves as the anchor, holding planets, asteroids, comets, and even the faintest specks of interplanetary dust within its dominion. But what gives it such power, and why does its influence extend so far? At the heart of the solar system lies its greatest mystery, the sun. This massive sphere of plasma, composed primarily of hydrogen and helium, fuels itself through nuclear fusion, a process that converts hydrogen into helium and releases immense amounts of energy. Every second, the sun produces enough energy to sustain humanity for 1 million years. Yet, only a fraction of that energy reaches Earth, and an even smaller portion is responsible for the life and ecosystems that thrive here. The sun is not just a star. It is a giver of life, a celestial guardian, and, at times, a volatile force capable of unleashing powerful solar flares that ripple through the solar system. Moving outward from the sun, we encounter the terrestrial planets: Mercury, Venus, Earth, and Mars. These rocky worlds share a common origin, but could not be more different in their characteristics. Mercury, the smallest and closest to the sun, is a world of extremes. Its surface alternates between searing heat and freezing cold, while its thin exosphere provides little protection against cosmic radiation. What forces shaped this enigmatic world, and why has it remained so geologically inactive for billions of years? Next, Venus, a planet shrouded in mystery and a thick, toxic atmosphere. Often called Earth's twin because of its similar size and composition, Venus is a scorching hellscape where temperatures soar high enough to melt lead. Its clouds of sulfuric acid and its runaway greenhouse effect make it a cautionary tale of planetary evolution. Could Venus have once been habitable? And if so, what triggered its transformation into the inferno we observe today? Then, there is Earth, the oasis of the solar system. Earth is unique, not just because it harbors life, but because it exists within a delicate balance. Its position within the so-called Goldilocks zone allows liquid water to persist, while its magnetic field shields it from harmful solar winds. But Earth's story is one of resilience. From its chaotic formation to its cycles of mass extinctions and recoveries, Earth has continuously evolved. Yet, amidst its stability, Earth remains fragile, its ecosystem sensitive to disruptions both natural and human-made. Mars, the red planet, looms next. Once thought to be barren and lifeless, Mars has captivated scientists with evidence of ancient rivers, lakes, and possibly even oceans. Today, it is a cold desert with thin air and harsh conditions. But beneath its surface lies a treasure trove of clues about its past and the potential for microbial life. Could humanity one day make Mars its second home? The exploration of Mars is not just a quest for knowledge, but a preparation for the challenges of interplanetary colonization. Beyond the terrestrial planets lies the asteroid belt, a vast collection of rocky remnants from the solar system's formation. Here, each asteroid tells a story of the chaotic early days when planets were still forming. Some, like Ceres, are large enough to be considered dwarf planets, while others are mere fragments of rock and metal. Why didn't these materials coalesce into a planet? And what secrets do they hold about the solar system's infancy? As we venture further, the solar system's true giants come into view. These gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, dominate the outer reaches with their sheer size and gravitational influence. Each one is a world of wonders, surrounded by moons that could rival planets in their complexity. But even as we admire their majesty, questions arise. Why does Jupiter emit more heat than it receives from the Sun? What powers Saturn's magnificent rings? Why is Uranus tipped on its side? And what fuels the intense storms on Neptune? These mysteries deepen as we approach the edge of the solar system, where dwarf planets like Pluto reside. Once considered the ninth planet, Pluto has become a symbol of how our understanding evolves with new discoveries. Beyond Pluto lies the Kuiper belt, a region filled with icy bodies and comets that act as time capsules, preserving the materials from the solar system's early days. Could these objects hold the keys to understanding the origins of life on Earth? Finally, we reach the Oort cloud, the solar system's outermost boundary. This distant region, filled with icy fragments, marks the point where the Sun's influence begins to wane, giving way to the vastness of interstellar space. Here, the solar system becomes a memory, a faint echo of its gravitational pull, and we are reminded of the fragility and transience of our cosmic neighborhood. But the solar system is not static. It is a living system, constantly evolving. Space missions like Voyager and New Horizons have expanded our horizons, offering glimpses of distant worlds and phenomena. Meanwhile, ambitious projects like the James Webb Space Telescope and upcoming missions to Mars and Europa promise to unravel more of the mysteries that surround us. As we explore the solar system, we are not just studying celestial objects. We are seeking answers to fundamental questions about our existence. Why are we here? Are we alone? And what lies beyond the solar system, waiting to be discovered? These questions drive our curiosity and fuel our desire to reach further, to understand more, and to embrace the unknown. This is the solar system, not just a collection of planets and stars, but a narrative of creation, survival, and discovery. Its story is our story, a tale of resilience, curiosity, and wonder. As we continue to uncover its secrets, we are reminded that in the vastness of space, we are connected not just to our planet but to the entire cosmos. The Sun, heart of the solar system. In the vast expanse of space, the Sun reigns as an unyielding force, its light and heat the lifeblood of our solar system. But what exactly is the Sun? How did it come to exist? And what role does it play in shaping the cosmic neighborhood we call home? To understand the solar system, we must first unravel the mysteries of its brilliant heart, a star that has captivated human imagination for millennia and continues to inspire all with its sheer power and influence. The Sun is more than a glowing orb in the sky. It is a celestial powerhouse, composed primarily of hydrogen and helium. It burns with a ferocity unmatched by any other object in our solar system. At its core, where temperatures exceed 15 million degrees Celsius, nuclear fusion transforms hydrogen atoms into helium, releasing an enormous amount of energy. This energy takes millions of years to travel from the Sun's core to its surface, where it radiates outward as light and heat. Every photon of light we see represents a journey through layers of plasma, turbulence, and unimaginable pressure. But the Sun's importance goes beyond its brilliance. Its gravitational pull binds the planets, moons, asteroids, and comets into a harmonious dance that has persisted for billions of years. Without the Sun's gravity, the solar system as we know it would cease to exist. Yet, for all its stability, the Sun is not static. It is a dynamic, living star that constantly evolves, pulsates, and, at times, erupts with violent flares and coronal mass ejections. These solar flares, bursts of charged particles and magnetic energy, can disrupt communications and power grids on Earth, reminding us of the Sun's immense power. The auroras that light up Earth's polar skies are beautiful reminders of this interaction. What triggers these eruptions, and how do they impact the delicate balance of the solar system? Scientists have dedicated decades to understanding the Sun's magnetic fields, which twist and snap like rubber bands under extreme tension, creating solar storms that ripple through space. The Sun's influence extends far beyond its immediate surroundings. The solar wind, a stream of charged particles emanating from its surface, flows outward to the edges of the solar system. This wind shapes the heliosphere, a protective bubble that shields the planets from harmful cosmic radiation. But even this shield has its limits. At the boundary of the heliosphere, known as the heliopause, the solar wind meets interstellar space, marking the edge of the sun's influence and the beginning of the galactic frontier. For much of human history, the sun was worshipped as a deity, revered for its life-giving energy. Ancient cultures built temples, aligned monuments, and even structured entire calendars around its movements. Yet, despite this reverence, the true nature of the sun remained elusive until the advent of modern science. Today, telescopes and space missions like the Parker Solar Probe and Solar Orbiter allow us to study the sun in unprecedented detail, revealing its inner workings and helping us predict its behavior. The sun's lifespan is finite, a humbling reminder of the impermanence of even the mightiest celestial bodies. Currently in its middle age, the sun is a stable main-sequence star, a phase that will last another 5 billion years. Eventually, it will exhaust its hydrogen fuel, expanding into a red giant and engulfing the inner planets, possibly including Earth. In its final stages, the sun will shed its outer layers, leaving behind a dense core, a white dwarf, that will slowly cool over billions of years. But for now, the sun remains steadfast, its energy nurturing the conditions for life on Earth. Without the sun, water would freeze, photosynthesis would cease, and Earth would become a cold, lifeless rock drifting in space. Yet, the sun's role extends far beyond Earth. It shapes the climates of other planets, drives the formation of comets, and even influences the evolution of life itself. Could the sun's variability, its cycles of increased and decreased activity, play a role in shaping the destinies of planets and the emergence of life? The sun is also a time machine. By studying it, we gain insights into the formation of the solar system and the processes that govern other stars in the universe. Our sun is not unique. It is one of billions of stars in the Milky Way galaxy. Yet, it holds a special place in our story, a constant companion in humanity's journey through the cosmos. As we gaze at the sun, protected by filters or through telescopes, we are reminded of its dual nature, a giver of life and a harbinger of potential destruction. It is a force of nature that we cannot control, only seek to understand. And in that understanding, we find not only knowledge but a profound sense of connection to the universe. The sun's story is our story, a tale of creation, endurance, and transformation. As we continue to explore its mysteries, we are reminded of its central role in the grand narrative of the solar system. Its light has guided us, its warmth has sustained us, and its energy has driven the cycles of life on Earth. The sun is not just a star. It is the heartbeat of our cosmic home, a constant reminder of the incredible forces that shape our existence. Mercury, the scorched enigma. As we leave the radiant embrace of the sun and journey outward, we encounter the solar system's smallest and innermost planet, Mercury. At first glance, this diminutive world seems unassuming, a cratered rock suspended in the void. Yet, beneath its stark, barren surface lies a story of extremes, contradictions, and unanswered questions. How did this planet, so close to the sun's unrelenting heat, come to be? What secrets does it hold about the solar system's chaotic beginnings? Mercury is a world of paradoxes. Despite its proximity to the sun, it is not the hottest planet in the solar system. That title belongs to Venus. Instead, Mercury endures wild temperature fluctuations, ranging from searing 430 degrees Celsius 800 degrees Fahrenheit during the day to a bone-chilling minus 180 degrees Celsius minus 290 degrees Fahrenheit at night. This dramatic swing is due to its lack of a substantial atmosphere to trap heat. Unlike Earth or Venus, which have thick layers of gas enveloping them, Mercury's atmosphere, or more accurately, its exosphere, is tenuous and transient, composed of atoms blasted off its surface by the sun's intense radiation and solar wind. This exosphere is more like a wisp of gas than a protective blanket, offering little insulation from the extremes of space. Mercury's surface tells a tale of relentless bombardment. It is heavily cratered, resembling Earth's moon, a testament to the intense impacts it endured during the solar system's early years. One of the most striking features is the Caloris Basin, a massive impact crater over 1,500 kilometers, 930 miles wide. This colossal scar hints at a violent past when collisions with asteroids and comets were commonplace. Surrounding the basin are peculiar terrain features, jumbled hills and valleys, created by the seismic waves that rippled across the planet during the impact. Yet Mercury is not merely a fossil of the past. It is geologically intriguing. Evidence suggests that volcanic activity once played a significant role in shaping its surface. Lava flows, now frozen in time, hint at a world that was once far more dynamic than it appears today. Even more surprising are the planet's mysterious hollows, shallow, irregular depressions with bright, reflective material. These features, unique to Mercury, remain a puzzle. Could they be the result of volatile materials sublimating into space? Or do they point to processes we have yet to comprehend? Mercury's core is another enigma. This small planet has a disproportionately large iron core, making up about 85% of its radius. This gives Mercury the highest density of any planet after Earth. Why does Mercury have such a massive core? One theory suggests that during its formation, Mercury may have collided with another protoplanet, stripping away much of its outer layers and leaving behind a metal-rich core. Alternatively, the intense heat from the young sun may have vaporized lighter materials, leaving a denser, iron-dominated structure. This massive core also generates a weak magnetic field, a feature that sets Mercury apart from Venus, Mars, and the Moon, which lack such fields. However, Mercury's magnetic field is only about 1% as strong as Earth's, and its origin remains a topic of intense study. Understanding why Mercury has a magnetic field, despite its slow rotation, could provide clues about the dynamics of planetary interiors and the conditions necessary for magnetic field generation. Mercury's orbit is another fascinating aspect of its nature. It has the most eccentric orbit of any planet, meaning its distance from the Sun varies significantly. This elliptical path, combined with its slow rotation, leads to strange phenomena. A day on Mercury, measured from one sunrise to the next, lasts 176 Earth days, which is longer than its year, which spans just 88 Earth days. This peculiar relationship between its rotation and orbit creates bizarre sunrises and sunsets for an observer on Mercury. Standing on its surface, you would witness the sun rise, pause, reverse its direction briefly, and then continue its ascent, a dance choreographed by celestial mechanics. Despite its harsh environment, Mercury has drawn humanity's attention for centuries. Early astronomers, including the Babylonians and Greeks, observed its swift movement across the sky, naming it after the fleet-footed Roman messenger god. Yet, for all its visibility, Mercury remained elusive. Its proximity to the Sun makes it difficult to observe from Earth, as it is often lost in the Sun's glare. This challenge persisted until modern space exploration provided new windows into its world. NASA's Mariner 10 mission, launched in the 1970s, was the first to visit Mercury, revealing a cratered surface and a thin exosphere. Decades later, the Messenger spacecraft, Mercury's surface, space environment, geochemistry, and ranging transformed our understanding of the planet. Orbiting Mercury from 2011 to 2015, Messenger mapped its surface in detail, analyzed its composition, and discovered surprising evidence of water ice in permanently shadowed craters near its poles. How could ice exist on such a scorched planet? These regions, shielded from sunlight, act as cold traps, preserving water molecules delivered by comets or formed through chemical interactions. As we peer into Mercury's depths, we begin to see its importance in the broader narrative of the solar system. Its proximity to the Sun makes it a laboratory for studying the effects of intense solar radiation and space weather. Its ancient surface, largely unaltered for billions of years, provides a window into the conditions of the early solar system, helping scientists piece together the puzzle of planetary formation. Mercury's unique features challenge our assumptions, forcing us to refine our models of how planets evolve over time. But for all we have learned, Mercury remains a world of unanswered questions. What drives its mysterious geological features? Why does it retain a magnetic field? And what can it teach us about the solar system's turbulent youth? Future missions, such as the joint European-Japanese Bepi-Colombo mission currently en route to Mercury, promise to shed new light on these mysteries, offering a closer look at this enigmatic world. Mercury, scorched yet icy, ancient yet dynamic, is a planet of extremes that defies simple categorization. It challenges our understanding of planetary science, beckoning us to explore further, to dig deeper, and to embrace the complexity of our solar system's innermost world. Its story is not just about survival in the sun's furnace, but about the resilience and adaptability of nature's creations in the face of unrelenting forces. Venus, Earth's fiery twin. As we move outward from Mercury, the next planet in the solar system emerges in a golden glow. Venus, often referred to as Earth's twin. Similar in size, mass, and composition, Venus might seem like Earth's celestial sibling. Yet, beneath its thick, reflective clouds lies a starkly different world, one of extremes and mysteries. Venus is a planet of contradictions, its surface a fiery, hellscape despite its ethereal appearance in the night sky. How did this seemingly similar world take such a divergent path from Earth? What secrets does it hold about planetary evolution and, perhaps, the future of our own planet? Venus is the brightest object in the sky after the sun and moon, earning it the title of morning star or evening star, depending on its position relative to Earth. Its beauty has inspired myths and legends across cultures, symbolizing love, fertility, and even war. Yet, as space exploration advanced, we uncovered the harsh realities hidden beneath its brilliance. Venus is a planet where temperatures reach an average of 475 degrees Celsius 900 degrees Fahrenheit, hot enough to melt lead. Its atmosphere, composed predominantly of carbon dioxide, is cloaked in thick clouds of sulfuric acid, trapping heat through a runaway greenhouse effect. This relentless heating makes Venus the hottest planet in the solar system, surpassing even Mercury, which is closer to the Sun. The story of Venus begins billions of years ago, when it likely resembled a younger Earth. Scientists believe Venus may have once had liquid water on its surface, perhaps even oceans. If so, what caused it to transform into the inferno we see today? The prevailing theory points to its greenhouse effect spiraling out of control. As the sun's energy heated the planet, water in Venus's atmosphere evaporated, breaking apart into hydrogen and oxygen molecules. Hydrogen, the lighter of the two, escaped into space, leaving the heavier carbon dioxide to dominate. Over time, the thick CO2 layer trapped more and more heat, creating the suffocating environment that defines Venus today. This runaway greenhouse effect makes Venus a cautionary tale for Earth. While our planet's climate is vastly different, Venus serves as a stark reminder of how fragile a planet's balance can be. Could Earth, under certain conditions, face a similar fate? Studying Venus allows scientists to refine their models of climate change, gaining insights that might help us protect our own world. Beneath its oppressive atmosphere, Venus's surface is both fascinating and hostile. Radar mapping, primarily by NASA's Magellan spacecraft, has revealed a landscape dominated by volcanic plains, vast lava flows, and large shield volcanoes. Venus's surface appears relatively young, with fewer impact craters compared to Mercury or the Moon. This suggests that volcanic activity may have resurfaced the planet within the past 500 million years. However, scientists are still debating whether Venus is geologically active today. Some studies point to possible hot spots and lava flows, while others suggest that the planet's surface is relatively stagnant. One of the most intriguing features of Venus is its lack of plate tectonics, a hallmark of Earth's geology. Instead, Venus seems to undergo a process of global resurfacing, where intense heat and pressure build beneath the crust until it catastrophically collapses, renewing the surface. This phenomenon, if confirmed, would make Venus unique among the rocky planets and could offer clues about its internal dynamics. Venus's atmospheric pressure at the surface is another extreme, about 90 times that of Earth, equivalent to being 900 meters, 3,000 feet, underwater. This immense pressure crushes anything that attempts to land on the planet. The Soviet Union's Venera missions in the 1970s and 1980s were the first to send probes to Venus's surface. These probes survived for only a short time, some mere minutes, before succumbing to the harsh conditions. Yet, they provided humanity's first glimpses of Venus's rocky, desolate terrain. While the surface of Venus is inhospitable, its upper atmosphere tells a different story. About 50 kilometers, 31 miles, above the surface, the temperature and pressure conditions are much more Earth-like. This has led to speculation about the possibility of microbial life in the Venusian clouds, where water droplets and organic molecules might coexist. In 2020, researchers announced the detection of phosphine gas in Venus's atmosphere, a potential biomarker. While the findings remain controversial and subject to further investigation, they have reignited interest in exploring Venus as a candidate for extraterrestrial life. Despite its proximity, Venus remains one of the least explored planets in the solar system. Part of the challenge lies in its extreme environment, which has historically made missions to Venus far more difficult than those to Mars or the Moon. However, recent advancements in technology and renewed interest in Venus have led to a resurgence of proposed missions. NASA's upcoming Da Vinci Plus and Veritas missions, along with ESA's Envision spacecraft, aim to study Venus's atmosphere, geology, and potential for past habitability in unprecedented detail. One of the enduring mysteries of Venus is its peculiar rotation. Venus rotates in the opposite direction to most planets in the solar system, a phenomenon known as retrograde rotation. Moreover, its rotation is incredibly slow. A day on Venus lasts 243 Earth days, longer than its year, which spans 225 Earth days. This unusual rotation has puzzled scientists for decades. Was Venus flipped upside down by a massive impact? Or did gravitational interactions with the Sun or other planets alter its spin? Understanding Venus's rotation could provide insights into the dynamics of planetary systems as a whole. As we continue to study Venus, its significance grows beyond planetary science. Venus serves as both a warning and a source of inspiration. Its extreme conditions highlight the delicate balance required for habitability, while its mysteries challenge us to think creatively and push the boundaries of exploration. Could understanding Venus help us unlock the secrets of distant exoplanets, some of which may face similar challenges to habitability? Venus, with its fiery surface and enigmatic past, stands as a testament to the diversity of worlds in the solar system. It is a planet of lessons, about resilience, transformation, and the delicate interplay of forces that shape a planet's destiny. As our spacecraft prepare to return to Venus, we find ourselves on the brink of new discoveries that could reshape our understanding of not just Venus, but the very mechanisms that govern planetary evolution. Earth, the Goldilocks planet. Amidst the swirling chaos of the solar system lies a singular oasis, a world perfectly positioned and uniquely equipped to harbor life as we know it. Earth, our home, is the only planet known to sustain complex ecosystems, a delicate balance of air, water, and land that has persisted for billions of years. But what makes Earth so special? Why does it stand apart in a cosmic neighborhood teeming with extremes? To uncover the answers, we must delve into the intricacies of our planet's formation, evolution, and the interconnected systems that sustain its fragile harmony. Earth occupies the so-called Goldilocks zone, a region around the Sun where conditions are just right for liquid water to exist. Too close, and water would evaporate under intense heat, as it did on Venus. Too far, and it would freeze into unyielding ice, as it has on Mars and beyond. Yet, location alone does not explain Earth's habitability. It is the combination of factors, its atmosphere, magnetic field, plate tectonics, and more, that creates a planet uniquely suited for life. Earth's journey began roughly 4.5 billion years ago, when a swirling disk of gas and dust coalesced into the rocky planet we call home. Early Earth was a hostile place, its surface a molten ocean of magma bombarded by asteroids and comets. Over millions of years, the planet cooled, and its crust solidified. Water, delivered by icy comets or formed from chemical reactions within the mantle, began to collect on the surface, creating the first oceans. These primordial waters, bathed in sunlight and enriched by volcanic minerals, became the cradle for life. One of Earth's most critical features is its atmosphere, a dynamic blanket of gases that protects the planet and supports life. Unlike Venus, with its thick carbon dioxide atmosphere, or Mars, with its thin, tenuous air, Earth's atmosphere strikes a delicate balance. Composed primarily of nitrogen and oxygen, it moderates temperatures, shields the surface from harmful solar radiation, and facilitates the water cycle. This balance was not always the case. In its early days, Earth's atmosphere was dominated by volcanic gases like carbon dioxide, methane, and ammonia. The rise of photosynthetic organisms, roughly 2.5 billion years ago, transformed the atmosphere by producing oxygen, a shift that set the stage for the proliferation of complex life. Earth's magnetic field is another unsung hero of habitability. Generated by the motion of molten iron in its core, this invisible shield deflects solar wind and cosmic radiation that would otherwise strip away the atmosphere. Without this protection, Earth could have suffered the same fate as Mars, whose lack of a magnetic field left its once thick atmosphere vulnerable to the relentless barrage of solar particles. The auroras, those mesmerizing lights near the poles, are visual reminders of the magnetic field's interactions with solar wind. The surface of Earth is a dynamic canvas, constantly reshaped by the process of plate tectonics. The movement of tectonic plates drives the formation of mountains, earthquakes, and volcanoes, cycling carbon and other elements between the surface and the interior. This geological activity plays a crucial role in regulating Earth's climate over geological timescales, ensuring that carbon dioxide levels remain within a range that prevents both runaway heating and catastrophic cooling. Water, the elixir of life, covers over 70% of Earth's surface. It is no coincidence that life on Earth is intrinsically tied to this remarkable molecule. Water's unique properties, its ability to dissolve a wide range of substances, its high specific heat capacity, and its solid form being less dense than its liquid form, create an environment conducive to life. The oceans, which harbor the vast majority of Earth's biodiversity, also act as climate regulators, absorbing and redistributing heat around the globe. Life on Earth is a story of adaptation and resilience. From the simplest single-celled organisms to the astonishing diversity of plants and animals that exist today, life has endured through mass extinctions, ice ages, and cataclysmic asteroid impacts. The fossil record reveals how life has repeatedly rebounded, evolving new forms and filling ecological niches in the wake of catastrophic events. Humanity, as a species, represents the latest chapter in this ongoing narrative, a species capable of pondering its origins and altering its environment on a global scale. Earth's biosphere, the thin layer where life thrives, is intricately interconnected. The atmosphere, oceans, land, and living organisms form a web of interactions that sustain life. Yet, this balance is fragile. Human activity, from deforestation to the burning of fossil fuels, is altering Earth's climate and ecosystems at an unprecedented rate. Rising global temperatures, melting ice caps, and extreme weather events are stark reminders of the impact we have on our planet. Will Earth systems be resilient enough to adapt, or will humanity's actions push them beyond a tipping point? Earth's moon, our constant companion, also plays a critical role in shaping the planet's environment. The moon stabilizes Earth's axial tilt, preventing wild swings in climate that could disrupt the delicate balance necessary for life. Its gravitational pull drives the tides, creating dynamic coastal ecosystems and influencing marine life cycles. The moon's origins, likely the result of a massive collision between early Earth and a Mars-sized protoplanet, also highlight the chaotic processes that shaped the solar system. From space, Earth appears as a breathtaking blue marble, its swirling clouds and shimmering oceans a stark contrast to the barren landscapes of neighboring planets. This perspective underscores not only the uniqueness of our world, but also its vulnerability. Earth is not isolated. It is part of a dynamic solar system, influenced by solar activity, asteroid impacts, and cosmic forces. The study of other planets, from Venus to Mars, offers insights into the factors that sustain or threaten life, helping us better understand and protect our home. As we look to the future, Earth faces both challenges and opportunities. Advances in science and technology offer the tools to mitigate environmental damage, harness renewable energy, and explore sustainable ways of living. At the same time, our growing understanding of Earth's place in the cosmos inspires a sense of stewardship, a recognition that our planet is not just a resource but a shared home for all life. Earth, the Goldilocks planet, is a world of wonder and complexity. It is a reminder of the extraordinary conditions required for life to flourish and the intricate interplay of forces that sustain it. As we continue to explore the cosmos, Earth remains our touchstone, a living laboratory for understanding the universe and our place within it. Have you ever looked at the sky and felt the desire to understand your place in the universe? On Beyond the Stars, every video is a window to infinity, a journey to connect you with the mystery and beauty of the cosmos. Subscribing to the channel is more than clicking a button. It's joining a movement to spread knowledge and inspire others to look at the stars with hope and curiosity. Be the light that guides others to discover the wonders of the universe. Subscribe, and let's explore the unknown together. The moon, our closest neighbor. Hanging in the night sky like a silent sentinel, the moon is Earth's constant companion, a celestial body whose influence extends far beyond its tranquil appearance. While it may seem modest compared to the vastness of space, the moon has shaped Earth's history in profound ways, from stabilizing its axial tilt to driving the tides that have nurtured life. But how did the moon come to be? What secrets lie hidden on its surface? And what role will it play in humanity's future exploration of the cosmos? The moon's origins trace back to a cataclysmic event in the early solar system. About 4.5 billion years ago, a Mars-sized protoplanet, often referred to as Theia, collided with the young Earth. The immense energy from this impact ejected a massive amount of debris into space, which eventually coalesced to form the moon. Evidence for this dramatic birth is found in the moon's composition, which closely mirrors that of Earth's crust and mantle. This shared heritage ties the moon and Earth together in a way that no other celestial body is linked to our planet. Over billions of years, the moon's surface has become a record of the solar system's history, its craters and basins preserving the marks of countless impacts. Unlike Earth, the moon lacks an atmosphere to erode or protect its surface, making it a pristine archive of cosmic events. The dark plains, or Maria, that dominate the moon's near side are vast fields of ancient lava flows, while the far side, shielded from Earth's view, is a rugged, heavily cratered landscape. This stark contrast between the two hemispheres raises intriguing questions about the moon's geological history and internal structure. One of the most striking features of the moon is its role in Earth's stability. Without the moon, Earth's axial tilt would vary wildly over time, leading to extreme climate shifts that could have hindered the development of life. The moon's gravitational pull also drives the tides, a force that has shaped coastal ecosystems and influenced the behavior of countless marine species. Even early humans were likely attuned to the rhythms of the tides and the moon's phases, incorporating its presence into mythology, agriculture, and navigation. The moon's relationship with Earth is dynamic. Tidal forces are causing the moon to drift away from Earth at a rate of about 3.8 centimeters, 1.5 inches per year. Over millions of years, this slow separation will lengthen Earth's days and alter the dynamics of the Earth-Moon system. But for now, the moon remains a vital force, a constant partner in Earth's journey through space. The moon's exploration has been one of humanity's greatest achievements. The Apollo missions of the 1960s and 70s brought humans to the moon's surface, allowing us to study it up close for the first time. These missions revealed not only the moon's geology, but also its potential as a stepping stone for deeper space exploration. Samples brought back from the moon have provided invaluable insights into its composition, confirming its connection to Earth and offering clues about the early solar system. In recent years, the moon has re-emerged as a focal point for space exploration. NASA's Artemis program aims to return humans to the moon, with plans to establish a sustainable presence on its surface. The moon's south pole, in particular, has drawn significant interest due to the presence of water ice in permanently shadowed craters. This resource could be critical for future missions, providing drinking water, oxygen, and even rocket fuel for journeys to Mars and beyond. The Moon also serves as a natural laboratory for scientific research. Its lack of an atmosphere and magnetic field makes it an ideal location for telescopes and instruments that can study the universe without interference from Earth's environment. By establishing observatories on the Moon, scientists could gain new insights into distant galaxies, dark matter, and the origins of the universe itself. Despite its proximity, the Moon still holds many mysteries. What lies beneath its surface? How did its internal heat dissipate, leading to its current geologically inactive state? And what can the Moon tell us about Earth's past, especially the period of heavy bombardment that shaped the inner planets? Ongoing missions, such as China's Chang'e program and India's Chandrayaan missions, continue to explore these questions, expanding our understanding of the Moon's composition and history. The Moon also has cultural significance that transcends its scientific importance. Throughout history, it has inspired art, poetry, and mythology, symbolizing change, renewal, and mystery. Its phases, from the slender crescent to the luminous full moon, have been woven into the fabric of human life, marking time and guiding traditions. Even today, the Moon remains a powerful symbol of exploration and aspiration, reminding us of humanity's potential to reach beyond Earth. As we look to the future, the Moon may play a crucial role in humanity's expansion into space. Its proximity makes it an ideal testing ground for new technologies and habitats, while its resources could support sustainable space exploration. The vision of an interconnected solar system, with the Moon as a hub for scientific research and interplanetary travel, is becoming increasingly tangible. The Moon, our closest neighbor, is more than just a celestial body in the night sky. It is a witness to Earth's history, a stabilizing force, and a beacon of possibility. As we continue to study and explore its surface, we deepen our understanding of the universe and our place within it. The Moon's story is, in many ways, inseparable from our own, a story of resilience, discovery, and the enduring connection between Earth and its lunar companion. Mars, the red frontier, rising in the night sky as a fiery red beacon. Mars has captured the imagination of humanity for millennia. Dubbed the Red Planet for its rust-colored surface, Mars is both a symbol of mythological war and a modern frontier for scientific exploration. It is a world of stark contrasts, ancient, yet brimming with potential for the future, harsh, yet holding tantalizing signs of habitability. What secrets does Mars harbor beneath its dusty plains and towering volcanoes? Could it once have supported life? And might it one day host human settlers? Mars is a terrestrial planet, similar to Earth in many ways, but profoundly different in others. With a diameter just over half that of Earth, it is smaller and less dense, with a gravity that is only about 38% of what we experience on Earth. Its thin atmosphere, composed primarily of carbon dioxide, provides little insulation, resulting in extreme temperature fluctuations. On Mars, daytime temperatures near the equator can reach a relatively mild 20 degrees Celsius 68 degrees Fahrenheit, but nights plunge to minus 100 degrees Celsius minus 148 degrees Fahrenheit. These conditions create an environment that is challenging for life as we know it, but not beyond the realm of possibility. One of Mars's most intriguing features is its surface, a testament to a dynamic past. The planet boasts the largest volcano in the solar system, Olympus Mons, which rises nearly 3 times the height of Mount Everest. Nearby lies Valles Marineris, a canyon system that dwarfs the Grand Canyon, stretching over 4,000 kilometers, 2,500 miles, across the Martian surface. These features hint at a planet that was once geologically active, shaped by volcanic eruptions, tectonic forces, and perhaps even flowing water. Water is central to Mars's allure and mystery. Today, the planet appears dry and desolate, but evidence suggests that liquid water once flowed across its surface. Ancient riverbeds, deltas, and lake basins are etched into the Martian terrain, pointing to a time billions of years ago when the planet had a thicker atmosphere and a climate capable of sustaining liquid water. The discovery of hydrated minerals and recurring slope lineae dark streaks that may indicate seasonal flows of briny water, further supports the idea that water has played a key role in Mars's history. The question of life on Mars is one of the most compelling in planetary science. If Mars once had liquid water and a more hospitable climate, could it have supported microbial life? And if so, could remnants of that life still exist, perhaps in subsurface reservoirs or beneath polar ice caps? These questions drive ongoing missions like NASA's Perseverance rover, which is exploring the Jezero crater, a site believed to have once been a lake. Perseverance is not only searching for signs of ancient life, but also collecting samples that will eventually be returned to Earth for detailed analysis. Mars is not only a target for robotic exploration, but also a focal point for human ambition. The idea of sending humans to Mars has shifted from the realm of science fiction to a concrete goal for space agencies and private companies. NASA's Artemis program aims to use the Moon as a stepping stone for eventual missions to Mars, while SpaceX envisions a future where humans establish a permanent presence on the red planet. Such endeavors face enormous challenges, from the months-long journey through space to the need for sustainable habitats and life support systems in Mars's harsh environment. Yet, the potential rewards are equally immense. Colonizing Mars would mark humanity's first step toward becoming a multiplanetary species, ensuring the survival of our civilization in the face of potential global catastrophes. Mars's polar regions add to its fascination. The planet's ice caps, composed of water ice and frozen carbon dioxide, expand and contract with the seasons. Beneath these caps lie layers of sediment and ice, preserving a record of Mars's climate history. Recent radar studies have suggested the presence of liquid water lakes beneath the southern ice cap, raising intriguing questions about the potential for life in these isolated environments. Despite its allure, Mars is a challenging world. Its thin atmosphere offers little protection from cosmic radiation and solar winds, while its surface is covered in fine dust that can pose risks to both machinery and human health. Dust storms, some of which can engulf the entire planet, are a formidable hazard, reducing visibility and disrupting solar-powered equipment. Yet, each challenge Mars presents is also an opportunity for innovation, pushing the boundaries of engineering, science, and human ingenuity. The exploration of Mars has a long and storied history. Early telescopic observations led to speculation about canals and intelligent life, fueling imaginations and inspiring works of science fiction. The reality, revealed by missions like Mariner, Viking, and more recently, Curiosity and Perseverance, is no less compelling. These robotic explorers have transformed our understanding of Mars, revealing a planet that is both alien and eerily familiar. With each new mission, we uncover more about Mars's geology, atmosphere, and potential for habitability, bringing us closer to answering the profound question: are we alone? Mars also holds lessons for Earth. Its transformation from a wetter, potentially habitable world to the arid landscape we see today offers insights into planetary evolution and climate change. By studying Mars, we not only learn about our neighbor, but also gain a deeper understanding of the forces that shape planets, including our own. As humanity prepares to take its first steps on Mars, the red planet stands as a symbol of possibility. It challenges us to dream bigger, reach farther, and confront the unknown. Mars is not just a destination. It is a proving ground for our species' resilience, curiosity, and determination. Whether through robotic probes or human footprints, the exploration of Mars is a journey of discovery that will expand our horizons and deepen our understanding of the cosmos. Mars, with its ancient rivers and towering volcanoes, its frozen poles and dust storms, is a world of contrasts and potential. It beckons us to explore, to learn, and to imagine a future where the red planet becomes not just a frontier, but a second home for humanity. The asteroid belt, a band of mysteries. Nestled between the orbits of Mars and Jupiter lies a vast and enigmatic region of the solar system known as the asteroid belt. Far from being an empty void, this zone is teeming with rocky remnants from the early days of planetary formation. These ancient fragments, ranging in size from tiny pebbles to dwarf planets like Ceres, hold the secrets of the solar system's chaotic beginnings. But why did these materials fail to coalesce into a full-fledged planet? What clues can they offer about the birth of worlds? And how does the asteroid belt fit into humanity's vision for space exploration and resource utilization? The asteroid belt is not as crowded as often depicted in science fiction. While it contains millions of asteroids, the vastness of space means that these objects are spread out over immense distances. Spacecraft passing through the belt, like NASA's Dawn mission or the Voyagers, are unlikely to encounter any obstacles unless they are deliberately aimed at a specific asteroid. Still, the belt is a treasure trove of information, its rocks serving as time capsules that preserve the conditions of the early solar system. The story of the asteroid belt begins more than 4.5 billion years ago, during the chaotic era of planetary formation. Within the swirling disk of gas and dust that surrounded the young sun, particles collided and stuck together, forming larger and larger bodies. In the region now occupied by the asteroid belt, these building blocks, called planetesimals, failed to form a single planet. The primary culprit was Jupiter's immense gravitational influence. As the gas giant grew, its powerful gravity stirred the region, preventing the planetesimals from merging and instead scattering them into a belt of debris. Today, the asteroid belt is home to a diverse population of objects, each with unique characteristics and stories to tell. Some asteroids are rich in metals like iron and nickel, remnants of the cores of larger bodies that were shattered in violent collisions. Others, known as carbonaceous asteroids, contain water and organic compounds, making them intriguing targets in the search for the building blocks of life. Could these asteroids have delivered water and organics to Earth during the planet's early history? This hypothesis, known as the Late Heavy Bombardment, suggests that asteroid impacts played a crucial role in shaping Earth's habitability. The largest object in the asteroid belt is Ceres, a dwarf planet that accounts for roughly a third of the belt's total mass. With a diameter of about 940 kilometers, 584 miles, Ceres is a world in its own right. Observations by NASA's Dawn spacecraft revealed that Ceres has a rocky core and a crust rich in water ice, with possible subsurface reservoirs of briny liquid. The discovery of mysterious bright spots on its surface, now identified as salt deposits, has sparked debates about ongoing geological activity. Could Ceres, with its hidden water and potential energy sources, harbor microbial life? Other notable residents of the belt include Vesta, a large asteroid with a differentiated structure similar to terrestrial planets, and Pallas, an asteroid with an unusually tilted orbit. These objects, along with countless smaller fragments, represent a rich diversity of compositions, shapes, and histories. Studying them helps scientists piece together the puzzle of how planets and moons form and evolve. The asteroid belt is not just a scientific curiosity, it is also a focus of growing interest for space exploration and resource utilization. Asteroids are rich in materials that could be invaluable for future space missions, including water for fuel production and metals for construction. Mining asteroids, once the realm of science fiction, is becoming a plausible goal as technology advances. Companies like Planetary Resources and Deep Space Industries have outlined plans to harvest asteroid resources, while space agencies are exploring the potential of asteroid materials to support long-term missions to the Moon, Mars, and beyond. One of the most intriguing aspects of the asteroid belt is its role as a frontier for exploration. Missions like NASA's OSIRIS-REx, which recently returned samples from the near-Earth asteroid Bennu, demonstrate the feasibility of studying these objects up close. Future missions may target the asteroid belt itself, seeking to unlock its mysteries and pave the way for human expansion into the solar system. By understanding the composition and behavior of asteroids, we not only learn about the past but also prepare for potential challenges, such as deflecting hazardous asteroids that could threaten Earth. Asteroids also hold a special place in humanity's imagination. Long before the modern era of space exploration, these minor planets were seen as celestial wonders. The first asteroid, Ceres, was discovered in 1801, followed by the identification of Pallas, Juno, and Vesta. Today, we know of hundreds of thousands of asteroids, each a unique fragment of the solar system story. Some, like Eros and Psyche, have been studied extensively, offering glimpses into their fascinating compositions and histories. Despite their diversity, Asteroids are united by their role as remnants of the past. They are the pieces that didn't quite make it into planets, frozen in time and space. By studying them, we gain a deeper understanding of the processes that shaped the solar system, from the formation of protoplanetary disks to the violent collisions that sculpted its final form. The asteroid belt, with its rocky inhabitants, is not a graveyard but a living laboratory, filled with insights about our cosmic origins. As humanity looks to the stars, the asteroid belt represents both a challenge and an opportunity. It is a reminder of the solar system's tumultuous past, a gateway to understanding planetary formation, and a potential stepping stone for the future of space exploration. Whether as scientific targets, sources of resources, or waypoints on journeys to distant worlds, the asteroids of this belt will play a crucial role in humanity's unfolding story among the stars. The asteroid belt, a band of mysteries encircling the sun, is more than a collection of rocks. It is a testament to the forces that shape the universe, a bridge between past and future, and a symbol of the endless possibilities that lie beyond Earth. Jupiter, king of the planets. As we journey farther from the sun, we encounter the colossal giant that dominates the outer solar system, Jupiter. Towering over all other planets in both size and influence, Jupiter is a cosmic marvel, a dynamic, swirling sphere of gas and storms that has shaped the evolution of the solar system itself. But what makes Jupiter so extraordinary? How did it come to wield such power? And what secrets are hidden within its colossal form and the diverse worlds that orbit it? Jupiter is the largest planet in the solar system, a gas giant with a mass more than 300 times that of Earth and a diameter 11 times greater. Its immense gravity has earned it the title of King of the Planets, and its presence has been both a protector and a disruptor of the solar system's delicate balance. By deflecting or capturing asteroids and comets, Jupiter has likely shielded Earth from numerous catastrophic impacts. At the same time, its gravitational influence has shaped the orbits of countless objects, creating regions like the asteroid belt and the Trojan asteroid clusters. Jupiter's composition sets it apart from the terrestrial planets. It is primarily made of hydrogen and helium, similar to the Sun, and its lack of a solid surface challenges our understanding of what it means to be a planet. The outer layers of Jupiter consist of thick clouds of ammonia and water vapor, creating the planet's iconic striped appearance. Beneath these clouds lies an ocean of liquid metallic hydrogen, a bizarre state of matter created by the immense pressure in Jupiter's interior. This metallic hydrogen generates Jupiter's powerful magnetic field, the strongest of any planet in the solar system. One of Jupiter's most striking features is the Great Red Spot, a colossal storm that has raged for at least 350 years. This swirling maelstrom, larger than Earth, is a high-pressure region where winds reach speeds of up to 432 kilometers, 268 miles per hour. But the Great Red Spot is not alone. Jupiter's atmosphere is a constant ballet of storms, jet streams, and turbulence. These dynamic weather patterns are fueled by the planet's internal heat, which radiates more energy than it receives from the sun. What drives this internal heat, and how does it sustain Jupiter's endless storms? Jupiter's moons are equally remarkable, forming a miniature planetary system of their own. With at least 95 known moons, Jupiter's diverse collection includes 4 major satellites known as the Galilean moons: Io, Europa, Ganymede, and Callisto. These worlds, discovered by Galileo Galilei in 1610, are as varied as they are fascinating. Io, the most volcanically active body in the solar system, is a world of fire and brimstone. Its surface is dotted with hundreds of active volcanoes, driven by the intense tidal forces exerted by Jupiter's gravity. These forces generate immense heat within Io, fueling eruptions that spew sulfur and lava across its surface. The constant reshaping of Io's landscape makes it a living laboratory for understanding planetary geology. Europa, in stark contrast, is a frozen world with a smooth, icy surface. Beneath its crust lies a global ocean of liquid water, kept warm by the same tidal forces that heat Io. This hidden ocean, containing more water than all of Earth's oceans combined, is one of the most promising places in the solar system to search for extraterrestrial life. Could microbial organisms thrive in the dark depths of Europa's ocean, sustained by hydrothermal vents or chemical reactions? Future missions, such as NASA's Europa Clipper, aim to answer this tantalizing question. Ganymede, the largest moon in the solar system, is a giant among giants. Larger than Mercury, it is the only moon known to have its own magnetic field, generated by a liquid iron core. Ganymede's surface is a mix of dark, ancient terrain and lighter, younger regions shaped by tectonic forces. Its subsurface ocean, sandwiched between layers of ice, adds to its intrigue as a potential habitat for life. Callisto, the outermost Galilean moon, is a world of craters and contrasts. Its heavily cratered surface is the oldest in the solar system, a relic of the early bombardment that shaped the planets and moons. Callisto's relatively low levels of geological activity make it an ideal target for studies of the solar system's past. Like Ganymede, it may also harbor a subsurface ocean, protected from Jupiter's intense radiation by its distance from the planet. Jupiter's role in the solar system extends far beyond its moons. Its powerful magnetic field creates an enormous magnetosphere that extends millions of kilometers into space, influencing the particles and radiation environment around it. This magnetosphere traps charged particles, creating intense radiation belts that pose challenges for spacecraft and future human exploration. Yet, these belts also provide a unique environment for studying the interaction between solar wind, planetary fields, and plasma physics. The exploration of Jupiter has been a cornerstone of planetary science. From the early flybys of Pioneer and Voyager to the detailed observations of the Galileo spacecraft, each mission has expanded our understanding of this giant planet and its moons. NASA's Juno spacecraft, currently in orbit around Jupiter, is unlocking new insights into the planet's interior structure, magnetic field, and atmospheric dynamics. By measuring the distribution of mass within Jupiter, Juno aims to reveal clues about the planet's formation and evolution. Jupiter's significance goes beyond its role in the solar system. It serves as a benchmark for studying exoplanets, particularly the gas giants that dominate many other planetary systems. By understanding Jupiter, we gain insights into the processes that govern the formation and behavior of planets around other stars. How common are planets like Jupiter? Do they play similar protective roles in their systems? Or do they disrupt the development of habitable worlds? Jupiter, the king of the planets, is a world of superlatives and mysteries. Its immense size and power, its dynamic atmosphere, and its diverse family of moons make it a cornerstone of our understanding of the solar system. As we continue to explore this gas giant, we are reminded of the complexity and wonder of the universe, and of the profound questions that still await answers in the swirling clouds of Jupiter and the icy oceans of its moons. Saturn, the jewel of the solar system. Drifting farther out into the solar system, we arrive at Saturn, a world so captivating that it has been dubbed the jewel of the solar system. With its stunning rings and an entourage of diverse moons, Saturn embodies the elegance and mystery of the cosmos. But beyond its beauty lies a wealth of scientific intrigue. How did Saturn's rings form? What secrets are hidden beneath its clouds and within its moons? And what role does this majestic gas giant play in the broader narrative of the solar system's evolution? Saturn, the sixth planet from the Sun, is the second largest in the solar system, surpassed only by Jupiter. It is a gas giant primarily composed of hydrogen and helium, with an average density so low that it could float in water, if a body of water large enough existed. Saturn's pale yellow hue, caused by ammonia crystals in its upper atmosphere, belies the turbulent and dynamic world beneath its serene appearance. The most iconic feature of Saturn is, of course, its rings. Stretching over 280,000 kilometers, 175,000 miles, from edge to edge, they are composed of billions of ice particles, ranging in size from tiny grains to massive boulders. These particles reflect sunlight, creating the dazzling appearance that has mesmerized observers since Galileo first viewed them through a telescope in 1610. But what are these rings, and where did they come from? Scientists believe Saturn's rings are relatively young, perhaps only 100 to 200 million years old, mere moments in cosmic terms. Their origin remains a topic of debate. One theory suggests the rings are remnants of a shattered moon or a comet that ventured too close to Saturn and was torn apart by tidal forces. Another hypothesis posits that the rings formed from the primordial material of the solar system, a relic of the planet's early history. Understanding the rings is more than a quest for knowledge about Saturn. It provides insights into the processes that govern planetary systems and the forces that shape celestial bodies. Saturn's atmosphere is a study in contrasts. From Earth, it appears calm and uniform, but up close, it reveals a world of swirling storms and jet streams. One of the most fascinating features is the hexagonal storm at the planet's North Pole. This enormous, six-sided vortex, first observed by the Voyager spacecraft, remains a scientific enigma. How did this unusual shape form, and why does it persist? Theories suggest it may result from the complex interplay of atmospheric currents, but definitive answers remain elusive. Beneath Saturn's atmosphere lies a vast ocean of metallic hydrogen, similar to Jupiter's interior. This ocean, under immense pressure, generates a powerful magnetic field that extends far into space. Saturn's magnetosphere, while not as intense as Jupiter's, is still one of the largest structures in the solar system, influencing the behavior of charged particles and interacting with the solar wind. Studying this magnetic environment provides valuable clues about the planet's internal structure and dynamics. Saturn's moons, more than 145 known to date, form a diverse and fascinating collection of worlds, each with unique characteristics and potential for scientific discovery. Among them, a few stand out as particularly extraordinary. Titan, Saturn's largest moon, is a world unto itself. Larger than Mercury and enveloped in a thick, orange-hued atmosphere rich in nitrogen and methane, Titan is the only moon in the solar system known to have clouds, rain, and liquid lakes on its surface. These lakes, however, are not filled with water, but with methane and ethane, creating an otherworldly hydrological cycle. Beneath Titan's icy crust lies a subsurface ocean of liquid water, making it a tantalizing target in the search for extraterrestrial life. Could primitive life forms exist in Titan's hidden ocean, or even in its surface lakes, despite the extreme cold? Enceladus, another of Saturn's moons, has captured the attention of scientists and the public alike. This small, icy world is home to active geysers that erupt from its south pole, spewing water vapor, ice particles, and organic compounds into space. These plumes, discovered by the Cassini spacecraft, are thought to originate from a subsurface ocean in contact with a rocky core, a potential recipe for life. Enceladus's geysers create a massive halo of material that contributes to one of Saturn's rings, blurring the line between the moon and the planet's iconic feature. Other moons, such as Iapetus with its stark two-tone coloration and Mimas with its resemblance to the Death Star, add to the richness of Saturn's story. Each of these moons offers a unique window into the processes that govern the formation and evolution of celestial bodies. The exploration of Saturn reached new heights with NASA's Cassini-Huygens mission, a collaboration with the European Space Agency and the Italian Space Agency. Launched in 1997, Cassini spent over 13 years orbiting Saturn, delivering breathtaking images and groundbreaking data before its dramatic plunge into the planet's atmosphere in 2017. The mission revealed the intricacies of Saturn's rings, the dynamic nature of its atmosphere, and the astonishing potential of its moons. The Huygens probe, which landed on Titan in 2005, provided humanity's first glimpse of the surface of this alien world, offering unparalleled insights into its chemistry and geology. Saturn's role in the solar system extends beyond its immediate environment. Its massive size and gravity have influenced the orbits of countless objects, including comets and asteroids. Saturn also serves as a natural laboratory for studying the behavior of gas giants, informing our understanding of similar planets and other star systems. The discovery of exoplanets has shown that gas giants like Saturn are common throughout the galaxy, making it a key reference point for comparative planetology. As we look to the future, Saturn continues to beckon with unanswered questions and untapped potential. Missions like Dragonfly, a rotorcraft set to explore Titan in the 2030s, promise to deepen our understanding of Saturn's moons and their potential for life. Meanwhile, Advancements in technology may one day allow us to probe the secrets of Saturn's interior or explore the possibility of harvesting resources from its rings and moons. Saturn, the jewel of the solar system, is more than a planet. It is a system of wonders, a source of inspiration, and a reminder of the incredible diversity of the cosmos. Its rings, moons, and storms challenge our perceptions and expand our horizons, inviting us to explore, to learn, and to marvel at the grandeur of the universe. Uranus, the tip giant. Beyond the orbit of Saturn lies Uranus, a planet that defies convention and challenges our understanding of the solar system. Known as the ice giant, Uranus is distinguished not only by its pale blue-green hue, but also by its extreme axial tilt, which causes it to roll through space like a barrel rather than spinning like a top. This peculiar orientation, combined with its frigid atmosphere and faint ring system, makes Uranus one of the most enigmatic planets in the solar system. But what caused its unusual tilt? What mysteries lie beneath its icy clouds? And how does this distant world fit into the broader narrative of planetary science? Discovered in 1781 by William Herschel, Uranus was the first planet identified with the aid of a telescope, marking a milestone in human exploration of the cosmos. Unlike the inner planets, which have been known since antiquity, Uranus appeared as a dim, bluish point of light that barely stood out against the backdrop of stars. Its discovery expanded the boundaries of the known solar system, opening the door to further discoveries in the outer reaches of space. Uranus is classified as an ice giant, a category it shares with its neighbor Neptune. While its composition includes hydrogen and helium, like Jupiter and Saturn, it also contains significant amounts of water, ammonia, and methane ices. Methane in its upper atmosphere absorbs red light, giving Uranus its distinct aquamarine color. But beneath this serene exterior lies a world of extremes. The defining characteristic of Uranus is its axial tilt. Unlike other planets, which rotate with axes roughly perpendicular to their orbital planes, Uranus's axis is tilted by an astonishing 98 degrees. This means that Uranus effectively orbits the Sun on its side, with its poles taking turns facing the Sun during its 84-year journey around the star. As a result, each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. This extreme orientation likely resulted from a massive collision with an Earth-sized object early in the planet's history, a violent event that reshaped Uranus's evolution. Uranus's atmosphere, while seemingly tranquil, harbors powerful winds and subtle weather patterns. Composed primarily of hydrogen, helium, and methane, it lacks the dramatic storms and bands seen on Jupiter and Saturn. However, observations from the Voyager 2 spacecraft and ground-based telescopes have revealed faint cloud features and seasonal changes, suggesting a more dynamic system than previously thought. Winds on Uranus can reach speeds of over 900 kilometers, 560 miles, per hour, swirling around the planet's equator. Beneath its icy clouds, Uranus is believed to have a slushy mantle of water, ammonia, and methane ices surrounding a rocky core. This mantle, under immense pressure, may contain a superionic water layer, a state of matter where water molecules break apart, allowing ions to flow freely, creating exotic electrical currents. This unique interior structure sets Uranus apart from the gas giants and offers a fascinating window into the behavior of materials under extreme conditions. Uranus also boasts a faint ring system, first discovered in 1977 when astronomers observed starlight dimming as it passed behind the planet. The rings, composed of dark, icy particles, are narrower and less prominent than Saturn's, but they add to the planet's mystique. Recent observations have hinted at the presence of additional faint rings, underscoring the complexity of Uranus's system. The planet is orbited by at least 27 known moons, most of which are named after characters from the works of Shakespeare and Alexander Pope. These moons vary widely in size and composition, with 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon, standing out as particularly intriguing. Miranda, the smallest of the major moons, features a patchwork of craters, ridges, and valleys, suggesting a history of intense geological activity. Some scientists speculate that tidal heating or ancient impacts may have reshaped its surface multiple times. Titania and Oberon, the largest moons of Uranus, exhibit heavily cratered surfaces, while Ariel appears to have the youngest surface, marked by smooth plains and fault lines. The diversity of Uranus's moons highlights the complex interactions between the planet and its satellites, shaped by gravitational forces and the planet's unique tilt. Uranus's magnetic field is another anomaly. Unlike Earth's magnetic field, which is roughly aligned with its rotational axis, Uranus's magnetic field is tilted at an angle of 59 degrees and offset from the planet's center. This irregularity creates a lopsided magnetosphere that interacts with the solar wind in unusual ways. Understanding this magnetic field could provide insights into the planet's interior structure and the dynamics of magnetic fields in other celestial bodies. Despite its distance from Earth, nearly 3 billion kilometers, 1.8 billion miles away, Uranus has been explored up close by only one spacecraft, Voyager 2. During its 1986 flyby, Voyager 2 revealed a wealth of information about the planet's atmosphere, rings, and moons, but it left many questions unanswered. Since then, advances in telescope technology have allowed astronomers to study Uranus in greater detail from afar, but a dedicated return mission remains a priority for planetary scientists. Future exploration of Uranus could unlock many of its mysteries. Proposed missions, such as an orbiter with atmospheric probes, aim to study the planet's composition, magnetic field, and moons in unprecedented detail. Understanding Uranus is not just about exploring a single planet. It is about expanding our knowledge of ice giants, a class of planets that may be common in other star systems. By studying Uranus, we can gain insights into the diversity of planetary systems and the processes that shape them. Uranus, the tipped giant, is a world of subtle beauty and profound mystery. Its unique characteristics challenge our assumptions about how planets form and evolve, offering a glimpse into the complexity of the universe. As we look to the future, Uranus beckons us to explore, to question, and to discover the secrets hidden within its icy depths and tilted orientation. Neptune, the windy blue world. At the outer edges of the solar system lies Neptune, a planet shrouded in an azure glow and cloaked in mystery. As the farthest planet from the Sun, Neptune is a world of extremes, where powerful winds roar through an icy atmosphere and dark storms swirl across its surface. Often referred to as the blue giant, Neptune challenges our understanding of planetary science with its dynamic weather, intense magnetosphere, and enigmatic moons. But what fuels its turbulent atmosphere in the cold, distant reaches of the solar system? How did Neptune form, and what secrets lie hidden in its depths? Discovered in 1846, Neptune was the first planet located through mathematical prediction rather than direct observation. Its existence was inferred from irregularities in Uranus's orbit, which hinted at the gravitational influence of another massive body. When astronomers pointed their telescopes toward the predicted position, they found Neptune, solidifying the power of mathematics in exploring the cosmos. This discovery was a turning point in astronomy, showcasing humanity's ability to uncover unseen worlds through logic and observation. Neptune is similar in composition to its neighbor Uranus, classifying it as an ice giant. It is primarily composed of hydrogen, helium, and methane, with the latter giving the planet its vivid blue color by absorbing red light. Beneath its outer atmosphere lies a dense, slushy mantle of water, ammonia, and methane ices surrounding a rocky core. Despite its distance from the Sun, Neptune emits more heat than it receives, a phenomenon that remains a puzzle. This internal heat likely drives the planet's dynamic atmosphere, creating some of the most extreme weather in the solar system. Neptune's atmosphere is a turbulent domain dominated by ferocious winds and massive storms. Wind speeds on Neptune can exceed 2,100 kilometers, 1,300 miles per hour, the fastest recorded in the solar system. These winds drive large, dark storm systems that appear and disappear over time. The most famous of these was the Great Dark Spot, observed by Voyager 2 during its 1989 flyby. Similar in size to Earth, this storm was a high-pressure system surrounded by fast-moving clouds of methane ice crystals. By the time the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished, replaced by other storms, a testament to the planet's ever-changing atmosphere. The planet's unique characteristics extend to its magnetosphere. Like Uranus, Neptune's magnetic field is tilted and offset from the planet's center, creating a complex and dynamic interaction with the solar wind. This irregular magnetosphere is likely generated by the motion of electrically conductive materials in Neptune's interior, but its exact mechanisms remain a mystery. Neptune's faint ring system is another area of intrigue. Composed of dark, icy particles, these rings are less prominent than Saturn's, but are nonetheless fascinating. The rings are not uniform. Some sections are denser, forming arcs that stand out against the background. Scientists are still trying to understand how these arcs remain stable, defying the expectations of ring dynamics. The rings may be relatively young, shaped by the gravitational influence of Neptune's moons or by collisions within the ring system itself. Speaking of moons, Neptune boasts a captivating collection of 14 known satellites, the most prominent of which is Triton. Triton is unlike any other moon in the solar system, with a retrograde orbit, meaning it moves in the opposite direction of Neptune's rotation. Triton is thought to be a captured object from the Kuiper belt, a distant region of icy bodies beyond Neptune. Triton's surface is a frozen wonderland, covered in nitrogen ice and dotted with cryovolcanoes that erupt plumes of nitrogen gas. These eruptions, observed by Voyager 2, suggest that Triton is geologically active, despite its frigid conditions. Triton's retrograde orbit and icy surface hint at a complex history. As a captured body, Triton's arrival likely disrupted Neptune's original moon system, ejecting or destabilizing smaller satellites. Its unique characteristics make it a prime target for future exploration. Could Triton's subsurface ocean, if it exists, harbor microbial life? What can this moon tell us about the processes that govern icy worlds and their potential for habitability? The story of Neptune's exploration is one of tantalizing glimpses. Voyager 2 remains the only spacecraft to visit Neptune, providing invaluable data during its brief flyby in 1989. Since then, astronomers have relied on telescopes like Hubble and ground-based observatories to study the planet. These observations have revealed seasonal changes in Neptune's atmosphere, despite its 165-year-long orbit around the Sun. However, many questions remain unanswered, underscoring the need for a dedicated mission to Neptune and its moons. A return to Neptune could transform our understanding of the outer solar system. Proposed missions, such as orbiters equipped with advanced instruments, aim to study Neptune's atmosphere, magnetic field, and ring system in unprecedented detail. Triton, with its active geology and potential for a subsurface ocean, is a particularly enticing target. By exploring Neptune and its moons, we can gain insights into the formation and evolution of ice giants, a class of planets that appear to be common in other star systems. Neptune also serves as a bridge to the even more distant realms of the solar system. Its position near the Kuiper belt places it at the edge of a region rich with icy objects and dwarf planets. Understanding Neptune's interactions with the Kuiper belt can provide clues about the dynamics of the outer solar system and the processes that shaped its structure. Neptune, the windy blue world, is a planet of extremes and enigmas. Its dynamic atmosphere, tilted magnetic field, and icy moons challenge our understanding of planetary science, inviting us to explore further. As we look toward the future, Neptune reminds us of the vastness and complexity of the cosmos, offering a glimpse into the mysteries that await beyond the familiar. Pluto and the dwarf planets. At the outermost reaches of the solar system lies a realm of icy worlds, where sunlight is faint and mysteries abound. Among these distant objects is Pluto, a celestial body once considered the 9th planet before its reclassification as a dwarf planet in 2006. But Pluto is not alone. It shares its region with a host of similar worlds that orbit the Sun in the icy expanse beyond Neptune. What makes these dwarf planets so fascinating? How do they fit into the story of the solar system's formation? And what secrets do they hold about the origins of our cosmic neighborhood? Pluto, discovered in 1930 by astronomer Clyde Tombaugh, captivated the world as the smallest and most distant planet in the solar system. Its reclassification as a dwarf planet sparked debate and interest, but far from diminishing Pluto's significance. This change highlighted its place in a broader population of icy bodies in the Kuiper belt. This region, a vast disc-shaped collection of objects, is a remnant of the early solar system, containing materials that have remained relatively unchanged for billions of years. Pluto's surface, revealed in stunning detail by NASA's New Horizons spacecraft in 2015, is a mosaic of geological wonders. Far from being a frozen wasteland, Pluto is a dynamic world with towering ice mountains, vast nitrogen plains, and a thin atmosphere of nitrogen, methane, and carbon monoxide. The heart-shaped feature known as Tombaugh Regio has become an iconic symbol of Pluto, its western lobe, a vast glacier of nitrogen ice, revealing evidence of ongoing geological activity. What drives this activity in such a cold environment? Scientists believe that internal heat, possibly generated by radioactive decay, could sustain this unexpected dynamism. One of Pluto's most intriguing features is its potential subsurface ocean. Beneath its icy crust, Pluto may harbor a layer of liquid water, kept from freezing by heat and pressure. If such an ocean exists, it raises tantalizing questions about the possibility of life in these distant realms. Could microbial organisms thrive in the hidden depths of a world so far from the sun's warmth? Pluto's unexpected complexity has transformed it from a planetary outlier to a key piece of the puzzle in understanding the diversity of worlds in the solar system. Pluto's relationship with its largest moon, Charon, adds another layer of intrigue. The two bodies are locked in a mutual orbit, with Charon's gravitational influence shaping Pluto's surface and atmosphere. Charon, with its own set of unique features, including a massive canyon system and a mysterious reddish polar cap, offers a window into the interactions between closely paired celestial bodies. The Pluto-Charon system is a binary planet system in all but name, their gravitational dance unlike any other in the solar system. But Pluto is just one member of a larger family of dwarf planets that inhabit the outer solar system. Haumea, Makemake, and Eris are three of the most prominent, each with distinct characteristics that challenge our understanding of planetary science. Haumea, for example, is an elongated, rapidly spinning world surrounded by a ring system, the first discovered around a dwarf planet. Its unusual shape and fast rotation suggest a violent past, possibly involving a massive collision that stripped away much of its original material. Makemake, slightly smaller than Pluto, is another Kuiper belt object with a bright, icy surface. Unlike Pluto, however, it lacks a significant atmosphere, raising questions about why these two similar-sized bodies have such different environments. Eris, often referred to as Pluto's twin, is slightly smaller but significantly more massive, with a surface coated in a reflective layer of frozen methane. Its discovery in 2005 led to the re-evaluation of what constitutes a planet, ultimately resulting in Pluto's reclassification. These dwarf planets, along with countless smaller Kuiper belt objects, are relics of the early solar system, preserved in the icy frontier beyond Neptune. Studying them provides insights into the processes that shaped the solar system's architecture, from the migration of the giant planets to the distribution of material in its outer regions. The Kuiper belt, often considered a fossilized remnant of planetary formation, holds clues about the building blocks that gave rise to planets, moons, and other celestial bodies. Pluto and its companions also serve as gateways to an even more distant realm, the Oort cloud. This theoretical shell of icy bodies encircles the solar system, extending halfway to the nearest stars. Comets that occasionally enter the inner solar system may originate in the Oort cloud, providing a direct link between these distant objects and Earth's history. Could similar icy bodies have delivered water and organic molecules to Earth during its formative years, seeding the conditions for life? By studying the Kuiper belt and dwarf planets, scientists hope to uncover answers to these profound questions. The exploration of Pluto and the dwarf planets is still in its infancy. New Horizons provided a groundbreaking first look at Pluto, but much of the Kuiper belt remains uncharted territory. Future missions to study these icy worlds could revolutionize our understanding of the outer solar system, shedding light on their composition, geology, and potential for life. The James Webb Space Telescope, with its advanced capabilities, is poised to study Kuiper belt objects in greater detail, offering glimpses into their surfaces and atmospheres. Pluto and the dwarf planets are more than icy outliers. They are vital pieces of the cosmic story, revealing the diversity and complexity of worlds that exist far from the Sun. Their unique features challenge our definitions of what it means to be a planet and expand our understanding of the processes that shape celestial bodies. As we continue to explore these distant realms, we are reminded of the richness and wonder of the solar system, where even the smallest worlds can hold the greatest mysteries. The Kuiper belt and beyond. Beyond the orbit of Neptune lies a vast and largely uncharted region of the solar system, the Kuiper belt. This expansive area, filled with icy remnants from the solar system's formation, serves as a gateway to the even more distant Oort cloud and the mysteries of interstellar space. Often compared to an archaeological site, the Kuiper belt holds ancient clues about the early solar system, acting as a time capsule for materials that have remained relatively unchanged for billions of years. But what exactly is the Kuiper belt? How does it influence the solar system? And what secrets lie hidden among its countless icy objects? The Kuiper belt, first hypothesized in the mid-20th century and confirmed in the 1990s, is a donut-shaped region that extends from about 30 to 55 astronomical units, AU, from the Sun. It is home to a diverse collection of objects, ranging from small icy bodies to dwarf planets like Pluto, Haumea, and Makemake. These Kuiper belt objects, KBOs, are composed of frozen water, methane, ammonia, and other volatile substances, providing a glimpse into the building blocks of the solar system. Unlike the asteroid belt, which lies between Mars and Jupiter, the Kuiper belt is much larger and more diffuse. The objects within it are remnants of the primordial disk of gas and dust that gave rise to the planets. However, the gravitational influence of the giant planets, particularly Neptune, prevented these objects from coalescing into larger bodies. Instead, they were left scattered in this distant, frozen region, preserved as they were during the solar system's earliest days. One of the most significant discoveries in the Kuiper belt is the diversity of its inhabitants. While Pluto remains the best-known KBO, many other objects exhibit unique characteristics that challenge our understanding of planetary science. Haumea, for instance, spins so rapidly that it has been stretched into an elongated shape, while Eris is more massive than Pluto and has a highly reflective surface. Each object tells a unique story about the forces that shaped it and the conditions that existed during its formation. The Kuiper belt is also a source of short-period comets, those with orbits lasting less than 200 years. These comets, such as Halley's Comet, are thought to originate in the Kuiper belt before being pulled inward by the gravitational influences of Neptune or other planets. As they approach the Sun, their icy surfaces sublimate, creating the characteristic tails that have fascinated humans for centuries. By studying these comets, scientists can gain insights into the composition of the early solar system and the processes that transported materials across vast distances. The exploration of the Kuiper belt reached a milestone with NASA's New Horizons mission. After its historic flyby of Pluto in 2015, New Horizons continued its journey into the Kuiper belt, encountering a small KBO named Arrokoth in 2019. This object, resembling a flattened snowman, provided a glimpse into the formation of small celestial bodies. Its two lobes, gently fused together, suggest that it formed through the slow collision of smaller building blocks, offering a snapshot of how planets and moons may have originated. While New Horizons has offered groundbreaking data, the Kuiper belt remains largely unexplored. Its vastness and the faintness of its objects make it challenging to study from Earth. However, advances in telescope technology, including the James Webb Space Telescope, are poised to change this. By observing the Kuiper belt in greater detail, scientists hope to uncover more about its composition, dynamics, and the interactions between its objects. The Kuiper belt also serves as a bridge to the even more distant Oort cloud, a spherical shell of icy bodies that surrounds the solar system and extends nearly halfway to the nearest stars. While no direct observations of the Oort cloud have been made, its existence is inferred from the behavior of long-period comets, which take thousands of years to complete their orbits. These comets, originating in the Oort cloud, provide a link between the solar system and the interstellar medium, hinting at the interactions between our Sun and its galactic environment. The Kuiper belt's significance extends beyond its role as a repository of icy objects. It has reshaped our understanding of the solar system's structure and dynamics. The discovery of large KBOs like Eris played a central role in the redefinition of what constitutes a planet, leading to the creation of the dwarf planet category and Pluto's reclassification. This debate underscored the complexity of the solar system and the need for flexible definitions that accommodate its diverse inhabitants. As we venture further into the Kuiper belt and beyond, we are confronted with profound questions about the origins and evolution of the solar system. How did the giant planets shape the distribution of materials in the outer regions? What role did the Kuiper belt play in delivering water and organics to Earth and other inner planets? And how do these distant regions connect to the broader processes at work in the galaxy? Future missions to the Kuiper belt could revolutionize our understanding of these icy worlds. Proposed spacecraft equipped with advanced instruments could survey multiple KBOs, study their surfaces and compositions, and search for signs of subsurface oceans or other intriguing features. These missions would not only expand our knowledge of the Kuiper belt, but also serve as stepping stones for exploring the Oort cloud and even interstellar space. The Kuiper belt, with its icy inhabitants and profound mysteries, represents a frontier of exploration and discovery. It is a reminder of the vastness and complexity of the solar system, where even the smallest and most distant objects hold the keys to understanding our cosmic origins. As we continue to study this frozen frontier, we are drawn closer to answering some of the most fundamental questions about the universe and our place within it. Comets, cosmic wanderers. Among the most captivating phenomena in the night sky, comets have inspired awe and curiosity for millennia. With their luminous tails stretching across the heavens, these celestial nomads are more than just beautiful spectacles. They are ancient messengers from the farthest reaches of the solar system. But what are comets? Where do they come from? And what can they tell us about the early solar system and the origins of life on Earth? Comets are icy bodies composed of a mixture of frozen water, gases, dust, and rocky materials. Often referred to as dirty snowballs, these small objects originate in the cold, distant regions of the solar system, primarily in the Kuiper belt and the Oort cloud. When a comet ventures closer to the Sun, the heat causes its icy surface to sublimate, releasing gas and dust that form a glowing coma around its nucleus and a distinctive tail that streams away from the Sun. The two primary types of comets are short-period comets, which have orbits lasting less than 200 years, and long-period comets, whose orbits can span thousands or even millions of years. Short-period comets, such as Halley's Comet, originate in the Kuiper belt, while long-period comets come from the Oort cloud. These objects, scattered by gravitational interactions, are pulled into the inner solar system by the Sun's gravity, becoming visible from Earth. The appearance of a comet is a dynamic and dramatic process. As it approaches the Sun, solar radiation heats its nucleus, causing the volatile ices to vaporize. The released gases and dust form a coma that can grow to thousands of kilometers in diameter. Solar wind and radiation pressure then shape the material into two distinct tails: the ion tail, composed of charged particles, and the dust tail, which reflects sunlight and curves gently due to the comet's motion. One of the most remarkable features of comets is their role as time capsules. Formed during the early stages of the solar system's evolution, comets preserve the original materials from the protoplanetary disk that surrounded the young Sun. By studying the composition of comets, scientists can gain insights into the conditions and processes that shaped the solar system more than 4.5 billion years ago. Comets may also hold clues about the origins of life on Earth. Some researchers hypothesize that cometary impacts delivered water and organic molecules, key ingredients for life, to the early Earth. The presence of complex organic compounds in comets, detected through spectroscopy and sample return missions, supports this idea. Could comets have been the cosmic delivery system that jump-started life on our planet? One of the most ambitious missions to study comets was the European Space Agency's Rosetta mission, which arrived at Comet 67P/Churyumov-Gerasimenko in 2014. Rosetta orbited the comet for over 2 years, sending back detailed images and data about its surface, composition, and activity. The mission's lander, Philae, made history by touching down on the comet's surface, despite its challenging terrain. Rosetta's findings revealed a wealth of information, including the presence of molecular oxygen and the complexity of the comet's organic chemistry. NASA's Stardust mission also advanced our understanding of comets by collecting samples from the coma of Comet Wild 2 and returning them to Earth in 2006. These samples contain tiny grains of material that predate the formation of the solar system, offering a direct link to the interstellar environment where the Sun was born. Such discoveries demonstrate the importance of comets as scientific gold mines, holding answers to questions about our origins. Not all interactions with comets are benign. Cometary impacts have shaped the history of Earth and other planets, sometimes with catastrophic consequences. The collision of Comet Shoemaker-Levy 9 with Jupiter in 1994 provided a dramatic reminder of the destructive potential of these objects. The impact, which left dark scars on Jupiter's atmosphere, demonstrated how comets can alter the dynamics of planetary systems. Despite their relatively small size, comets have had an outsized impact on human culture. Throughout history, comets have been seen as omens, their sudden and dramatic appearances inspiring myths, fears, and even political decisions. In more recent times, they have become symbols of discovery and exploration, capturing the imagination of scientists and the public alike. The study of comets continues to be a priority for planetary science. Missions like the proposed Comet Interceptor aim to study a pristine comet entering the inner solar system for the first time, offering a rare opportunity to observe an object that has remained largely untouched since its formation. Such missions could expand our understanding of the diversity of comets and their role in the evolution of the solar system. Comets also hold potential for future space exploration and resource utilization. Their volatile materials, such as water ice, could be harvested to produce fuel and support human missions to distant destinations. By unlocking the resources of comets, humanity could take significant steps toward becoming a spacefaring civilization. As we look to the future, comets remain a source of wonder and scientific inquiry. These cosmic wanderers, with their luminous tails and ancient origins, remind us of the interconnectedness of the solar system and the profound mysteries that lie beyond our planet. Whether as messengers from the past, agents of planetary evolution, or harbingers of future exploration, comets continue to inspire and challenge our understanding of the universe. Oort cloud, the edge of the solar system. Far beyond the planets and the Kuiper belt lies one of the most enigmatic regions of the solar system, the Oort cloud. This distant, spherical shell of icy bodies marks the boundary of the Sun's gravitational influence and the beginning of interstellar space. While no direct observations of the Oort cloud have been made, its existence is inferred from the behavior of long-period comets that occasionally grace the inner solar system. What is the Oort cloud, and why is it considered one of the final frontiers in our quest to understand the solar system? The Oort cloud is theorized to be a vast reservoir of comets and icy bodies, extending from about 2,000 to 100,000 astronomical units, AU, from the Sun. To put that in perspective, the outer edge of the Oort cloud is more than halfway to the nearest star system, Alpha Centauri. The sheer scale of this region makes it challenging to study, and its objects are so distant and faint that they remain invisible to even the most powerful telescopes. The origins of the Oort cloud trace back to the formation of the solar system, over 4.5 billion years ago. During the early stages of planetary formation, countless small icy bodies were scattered by the gravitational interactions of the giant planets. Some of these objects were ejected from the inner solar system entirely, while others settled into distant, stable orbits, forming the Oort cloud. This process, driven by the chaotic dynamics of the young solar system, effectively created a celestial boundary that encapsulates the Sun's gravitational domain. The Oort cloud is divided into two regions: the inner Oort cloud, or Hill's cloud, which is denser and closer to the Sun, and the outer Oort cloud, which forms a diffuse spherical shell. The objects in these regions are thought to be composed of volatile materials, including water, methane, ammonia, and other ices. These frozen remnants are believed to be some of the oldest and most pristine objects in the solar system, preserving the conditions of its early history. The most direct evidence for the Oort cloud comes from long-period comets, those with orbits lasting thousands or even millions of years. These comets, such as Comet Hale-Bopp, are believed to originate in the Oort cloud, their orbits perturbed by the gravitational influence of nearby stars, galactic tides, or interactions within the cloud itself. Once dislodged, these comets make their long journey toward the inner solar system, providing scientists with a rare opportunity to study material from the solar system's distant reaches. One of the key mysteries surrounding the Oort cloud is its relationship with the broader galaxy. As the solar system orbits the Milky Way, it encounters varying gravitational forces from nearby stars, molecular clouds, and the galactic disk. These interactions can perturb the orbits of Oort cloud objects, sending some of them inward as comets, while others are ejected into interstellar space. Such dynamics highlight the interconnectedness of the solar system and its galactic environment. The Oort cloud also raises intriguing questions about the boundaries of the solar system. Where does the sun's influence truly end, and where does interstellar space begin? The heliosphere, a bubble of solar wind that extends beyond the planets, marks one boundary, but the Oort cloud represents a far more distant frontier. Understanding this region is critical for defining the extent of our cosmic neighborhood and its interactions with the interstellar medium. Despite its remoteness, the Oort cloud plays a significant role in shaping the history of the solar system. Cometary impacts, thought to originate from Oort cloud objects, have influenced planetary evolution and may have delivered water and organic compounds to the early Earth. These collisions, while potentially catastrophic, also highlight the importance of the Oort cloud as a reservoir of materials that could provide insights into the building blocks of life. The exploration of the Oort cloud remains a daunting challenge due to its vast distance and the faintness of its objects. However, future missions to study long-period comets could provide indirect evidence about the cloud's composition and dynamics. Advanced telescopes, such as the Vera C. Rubin Observatory, are expected to revolutionize our understanding of the outer solar system by detecting more distant objects and mapping their orbits with unprecedented precision. The concept of the Oort cloud also intersects with the search for Planet 9, a hypothetical planet that could explain certain anomalies in the orbits of distant Kuiper belt objects. If such a planet exists, it might influence the structure of the inner Oort cloud, offering an indirect way to study this elusive region. Could Planet 9 be the missing link in our understanding of the solar system's outermost boundaries? As humanity looks to the stars, the Oort cloud serves as a reminder of the solar system's vastness and complexity. It represents the ultimate boundary of our home system, a region where the familiar laws of planetary science meet the uncertainties of interstellar space. The study of the Oort cloud is not just about understanding the solar system's edges. It is about exploring the connections between our sun, its planetary family, and the galaxy as a whole. The Oort cloud, distant and mysterious, is both a frontier and a bridge to the broader cosmos. It challenges us to push the limits of exploration and to seek answers to questions that extend far beyond our immediate surroundings. As we continue to study this icy boundary, we are reminded of the endless possibilities that lie within the solar system and beyond. Solar system formation, a stellar nursery. To understand the solar system as it exists today, we must travel back in time to its birth. A journey that begins in a swirling cloud of gas and dust within a stellar nursery. About 4.6 billion years ago, a series of cosmic events set the stage for the formation of the Sun and its family of planets, moons, and other celestial bodies. But how did this intricate system come to be? What forces shaped the solar system's architecture? And what clues remain hidden within its structure and composition? The story of the solar system begins in a molecular cloud, a vast, cold region of interstellar space rich in hydrogen, helium, and trace amounts of heavier elements. These clouds are the birthplaces of stars, where gravity gathers material into dense clumps. In one such clump, a disturbance, perhaps the shockwave from a nearby supernova, triggered a gravitational collapse. As the material fell inward, it began to spin, conserving angular momentum and forming a rotating disk of gas and dust. At the center of this protostellar disk, the pressure and temperature increased dramatically, igniting nuclear fusion and giving birth to the Sun. This newly formed star became the anchor of the solar system, its gravity shaping the orbits of the surrounding material. Meanwhile, in the cooler outer regions of the disk, smaller clumps of gas and dust began to collide and stick together, forming planetesimals, the building blocks of planets. The process of accretion played a crucial role in shaping the early solar system. These planetesimals grew larger through repeated collisions, eventually forming protoplanets. In the inner solar system, closer to the Sun, intense heat prevented lighter elements like hydrogen and helium from condensing. Instead, rocky materials dominated, giving rise to the terrestrial planets: Mercury, Venus, Earth, and Mars. Farther out, beyond the frost line where temperatures were colder, ices and gases could condense, allowing the formation of the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. Jupiter, the largest planet, exerted a powerful gravitational influence during this period, shaping the distribution of material throughout the solar system. Its presence likely prevented the formation of a planet in the region now occupied by the asteroid belt, scattering rocky debris and creating the dynamic environment we observe today. Similarly, the outer planets played a key role in sculpting the Kuiper belt and the distant Oort cloud, flinging icy bodies into these remote regions. As the planets took shape, they continued to interact with the remaining gas and dust in the protoplanetary disk. This phase of planetary migration had a profound impact on the solar system's architecture. Evidence suggests that the giant planets moved significantly from their initial positions, with Jupiter and Saturn's interactions possibly triggering a cascade of gravitational effects that reshaped the orbits of other planets and smaller bodies. One of the most significant events in the early solar system was the Late Heavy Bombardment, a period of intense asteroid and comet impacts approximately 4 billion years ago. This chaotic era, likely caused by the shifting orbits of the giant planets, left its mark on the surfaces of the Moon, Mercury, and other celestial bodies. These impacts not only reshaped the young planets, but also delivered water and organic materials to Earth, setting the stage for the emergence of life. While much of the gas and dust from the protoplanetary disk was either swept away by the solar wind or incorporated into the forming planets, some remnants remain. The asteroid belt, Kuiper belt, and Oort cloud are all relics of this formative period, preserving the materials and conditions of the early solar system. By studying these regions, scientists can piece together the story of how the solar system came to be. The Sun, too, carries the legacy of the solar system's formation. Its composition, primarily hydrogen and helium with traces of heavier elements, reflects the materials available in the protostellar cloud. The Sun's magnetic activity and solar wind have shaped the environment of the inner solar system, influencing the atmospheres and surfaces of the terrestrial planets. The Moon provides another vital chapter in the story of solar system formation. Current evidence suggests that the Moon formed as a result of a colossal impact between the young Earth and a Mars-sized body known as Theia. The debris from this collision coalesced to form the Moon, a process that left Earth with a tilted axis and stable climate, both crucial for the development of life. Advances in technology have allowed scientists to refine their understanding of the solar system's formation. Missions like the Hubble Space Telescope and the James Webb Space Telescope have observed protoplanetary disks around young stars, offering glimpses of processes similar to those that shaped our own solar system. These observations provide a cosmic context, revealing that the solar system is not unique, but one of countless planetary systems scattered throughout the galaxy. Despite this progress, many questions remain. What triggered the initial collapse of the protostellar cloud? How did the specific configurations of the planets arise? And what role did the migration of the giant planets play in the development of the inner solar system? These mysteries drive ongoing research, as scientists use a combination of computer simulations, laboratory experiments, and space missions to uncover the answers. The formation of the solar system is more than a story of cosmic mechanics. It is a tale of creation, resilience, and transformation. It is a reminder of the interconnectedness of all celestial bodies and the delicate balance of forces that govern their evolution. As we study the origins of the Sun, planets, and smaller bodies, we gain not only a deeper understanding of the solar system, but also insights into the processes that shape planetary systems throughout the universe. The solar system, with its intricate dance of planets, moons, and asteroids, is a testament to the power of gravity, the endurance of time, and the complexity of the cosmos. Its formation is a story written in the stars, a narrative that continues to unfold as we explore its farthest reaches and unravel the mysteries of its birth. Planetary rings, nature's cosmic jewelry. One of the most mesmerizing features of the solar system is the phenomenon of planetary rings. Those delicate, shimmering bands encircling giant planets like Saturn, Jupiter, Uranus, and Neptune. Often referred to as cosmic jewelry, these rings are not only visually stunning, but also scientifically fascinating, offering insights into the dynamics of planetary systems and the forces that shape them. What are planetary rings made of? How did they form? And why do some planets possess such intricate systems while others do not? Exploring these questions reveals a story as dynamic as the rings themselves. Saturn is undoubtedly the most famous ring planet, with its iconic system of rings visible even through small telescopes. Stretching over 280,000 kilometers, 175,000 miles, from the planet, but only a few meters thick, Saturn's rings are composed primarily of water ice, along with smaller amounts of rocky debris and dust. Their extraordinary brightness and symmetry have captivated observers for centuries, yet their true nature remained a mystery until the advent of modern telescopes and spacecraft. The Voyager missions of the 1980s revolutionized our understanding of Saturn's rings, revealing their intricate structure. The rings are divided into several major sections, labeled A, B, C, and so on, separated by gaps like the famous Cassini division, a 4,800-kilometer wide, 3,000-mile wide region largely devoid of material. Within the rings, countless particles range in size from tiny grains of dust to massive boulders, all orbiting Saturn at different speeds. These particles are governed by the planet's immense gravity and shaped by the gravitational influence of its moons. But what created Saturn's rings? One leading theory suggests that they formed from the remnants of a moon or comet that ventured too close to Saturn and was torn apart by tidal forces. Alternatively, the rings may be primordial, composed of material that never coalesced into a moon during the planet's formation. Recent studies indicate that Saturn's rings may be relatively young, possibly only 100 to 200 million years old, an eye blink in cosmic terms. Their age raises intriguing questions about whether ring systems are transient features, appearing and disappearing over the lifetimes of planets. While Saturn's rings steal the spotlight, other planets also possess ring systems, though they are less prominent and more subtle. Jupiter's rings, for instance, are faint and composed mostly of dust particles ejected from its moons by micrometeorite impacts. Discovered by the Voyager spacecraft, these rings are nearly invisible, their presence only detected by the way they scatter light. Uranus, too, boasts a system of rings, discovered in 1977 when astronomers observed a star briefly dimming as it passed behind the planet, a phenomenon caused by the rings blocking its light. Uranus's rings are darker and narrower than Saturn's, consisting primarily of rocky and icy debris. Their origin remains a mystery, though they may have formed from the remnants of shattered moons or material left over from the planet's violent tilting event, which gave Uranus its extreme axial tilt. Neptune's rings, like those of Uranus, are faint and composed of dark material, making them difficult to observe. However, they are unique in their structure, featuring arcs, denser regions of material that stand out against the rest of the rings. Scientists are still puzzled by how these arcs remain stable, as gravitational forces would typically cause the material to spread evenly around the planet. The study of planetary rings offers a window into the forces that govern celestial systems. Rings are not static. They are dynamic environments where particles collide, clump together, and are gradually eroded by micrometeoroid impacts and interactions with the planet's magnetic field. Over time, material from the rings may either spiral inward, falling onto the planet, or be ejected into space. This continual reshaping makes ring systems both transient and ever-evolving. Planetary rings are also influenced by their host planets' moons, which act as shepherds, confining ring particles within specific boundaries. For instance, Saturn's moons Prometheus and Pandora shepherd the narrow F ring, their gravitational interactions creating waves and braids within the ring structure. These intricate dynamics highlight the interplay between moons and rings, revealing the delicate balance of forces at work. Beyond the solar system, observations of distant exoplanets have hinted at the existence of ring systems around other worlds. These rings, if confirmed, could be orders of magnitude larger than those in our solar system, challenging our understanding of how rings form and persist. The study of exoplanetary rings is still in its infancy, but it underscores the potential for rings to exist in a variety of environments, shaped by the unique characteristics of their systems. Planetary rings also hold clues about the early solar system. By studying their composition and structure, scientists can infer the conditions that existed during the planet's formation. The rings of Saturn, for example, contain traces of organic molecules, hinting at the complex chemistry that may have been present in the protoplanetary disk. Rings can also serve as analogs for the disks of material that surround young stars, offering a scaled-down model for understanding how planets form within these environments. Despite their ethereal beauty, rings may not be permanent features. As they evolve and lose material, their fate is tied to the gravitational forces and interactions that shape them. Will Saturn's rings eventually disappear, leaving the planet bare? And are we witnessing a rare moment in the solar system's history where multiple planets still possess these transient adornments? The exploration of planetary rings continues to captivate scientists and the public alike. Missions like Cassini, which spent over a decade studying Saturn and its rings, have provided unparalleled insights into these structures, revealing their complexity and dynamism. Future missions to the outer planets may uncover even more about the origins and evolution of rings, shedding light on their role in the solar system and beyond. Planetary rings, nature's cosmic jewelry, are a testament to the intricate forces that shape the universe. They remind us of the beauty and complexity of the solar system, where even the smallest particles can come together to create structures of extraordinary elegance. As we continue to explore and study these rings, we are reminded of the delicate balance that governs the cosmos and the enduring wonder of the universe. Exoplanetary comparisons, lessons from other systems. In recent decades, the discovery of exoplanets, planets orbiting stars beyond our sun, has revolutionized our understanding of the cosmos. From gas giants many times the size of Jupiter to rocky worlds orbiting in the habitable zones of their stars, exoplanets come in a dazzling variety of sizes, compositions, and orbital configurations. But how do these alien worlds compare to the planets in our solar system? What can we learn from their diversity, and how do they challenge our understanding of planetary formation and evolution? The first confirmed detection of an exoplanet occurred in 1992, when astronomers discovered planets orbiting a pulsar, a rapidly spinning neutron star. These bizarre worlds defied expectations, as pulsars were not thought to be hospitable environments for planets. Just a few years later, the discovery of 51 Pegasi b, a hot Jupiter orbiting a sun-like star, opened the floodgates for exoplanet research. Since then, thousands of exoplanets have been identified, each expanding our understanding of the potential diversity of planetary systems. One of the most striking differences between exoplanetary systems and our solar system is the prevalence of hot Jupiters. These gas giants orbit extremely close to their stars, completing orbits in just days or weeks. Their proximity results in searing temperatures and puzzling orbital dynamics. How did these massive planets end up so close to their stars? The prevailing theory suggests that they formed farther out, like Jupiter, but migrated inward due to interactions with the protoplanetary disk or neighboring planets. This process, known as planetary migration, has profound implications for the evolution of planetary systems, including our own. The discovery of super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, has added another layer of intrigue. These planets are among the most common types detected in other systems, yet they are absent from our solar system. What accounts for this discrepancy? Scientists speculate that differences in the formation environment, such as the availability of materials or the timing of planetary migration, may explain why these intermediate-sized worlds dominate exoplanetary populations. Exoplanet atmospheres have become a key focus of research, thanks to advances in observational technology. By studying the light that passes through a planet's atmosphere as it transits its star, astronomers can identify the chemical fingerprints of gases like water vapor, methane, and carbon dioxide. These analyses have revealed atmospheres rich in exotic compounds, such as titanium oxide and sulfuric acid, on planets with extreme temperatures. Understanding these atmospheres provides clues about planetary composition, climate, and the potential for habitability. Habitable zone planets, those located at the right distance from their stars to support liquid water, are particularly tantalizing. The discovery of Earth-sized planets in the habitable zones of stars like Proxima Centauri and TRAPPIST-1 has fueled the search for life beyond Earth. However, not all habitable zone planets are created equal. Factors such as atmospheric composition, magnetic fields, and geological activity play crucial roles in determining whether a planet can truly support life. The architecture of exoplanetary systems often defies expectations based on the solar system. Many systems feature planets with highly elliptical orbits, closely packed configurations, or inclinations that differ significantly from the plane of their star's equators. These diverse arrangements challenge traditional models of planetary formation, which were largely based on the relatively orderly configuration of our solar system. Could the solar system be an outlier? Or do these systems reflect the chaotic processes that govern planetary evolution? Studying exoplanets also provides a new perspective on the solar system. By comparing our planets to those in other systems, we can better understand the factors that shape their formation and evolution. For instance, the absence of hot Jupiters in our solar system may have allowed the terrestrial planets to form and remain stable in the inner regions. Similarly, the presence of Jupiter and Saturn likely played a role in shaping the orbits of smaller bodies and protecting Earth from frequent cometary impacts. Exoplanet research has also advanced our understanding of planetary migration and its effects on habitability. In many systems, the inward migration of giant planets may have disrupted the formation of smaller, rocky planets, or ejected them entirely. The relatively calm environment of the solar system's inner regions may have been a key factor in the development of life on Earth. Could this make our system rare? Or are we simply uncovering a small sample of planetary systems that resemble ours? The study of exoplanets has also revealed planets in extreme environments, such as rogue planets drifting through interstellar space without a host star. These orphan worlds challenge our notions of what constitutes a planet and raise questions about their origins and potential for hosting life. Similarly, planets orbiting binary or even trinary star systems, like the iconic Tatooine from Star Wars, demonstrate the adaptability of planetary formation in diverse gravitational environments. Future missions promise to revolutionize our understanding of exoplanets. The James Webb Space Telescope (JWST) will provide unprecedented detail about exoplanet atmospheres, enabling the search for biosignatures, chemical signs of life. The European Space Agency's Ariel mission aims to survey the atmospheres of hundreds of exoplanets, while next-generation ground-based telescopes like the Extremely Large Telescope (ELT) will offer direct imaging of distant worlds. Together, these efforts will deepen our understanding of exoplanet diversity and their potential for habitability. Exoplanets have expanded our understanding of the cosmos, revealing a universe teeming with worlds of every imaginable variety. Their diversity challenges our assumptions about planetary systems and offers new insights into the processes that shape them. As we continue to explore these alien worlds, we are reminded that the solar system is just one chapter in a much larger story, a story that spans billions of years, countless stars, and the vastness of space. Space missions, probing the unknown. From the earliest robotic explorers to the advanced spacecraft of today, space missions have been humanity's window into the mysteries of the solar system. These ambitious endeavors have allowed us to venture far beyond Earth, visiting planets, moons, asteroids, and even interstellar space. But how have these missions shaped our understanding of the cosmos? What challenges do they face? and what discoveries still await as we continue to push the boundaries of exploration. The journey began in the mid-20th century with the launch of Sputnik 1 by the Soviet Union in 1957. This small satellite marked humanity's first step into space, igniting a race to explore beyond Earth's atmosphere. Just a few years later, the United States achieved another milestone with the Apollo program, culminating in the Apollo 11 moon landing in 1969. The image of Neil Armstrong stepping onto the lunar surface remains one of the most iconic moments in human history, symbolizing our ability to reach beyond our home planet. While the Apollo missions focused on human exploration, robotic missions have been the workhorses of solar system exploration. The early Pioneer and Voyager spacecraft paved the way for humanity's understanding of the outer planets. Launched in the 1970s, Voyager 1 and Voyager 2 conducted historic flybys of Jupiter, Saturn, Uranus, and Neptune, sending back breathtaking images and groundbreaking data. Even now, decades later, both Voyagers continue to transmit information as they traverse interstellar space, providing the first direct observations of the heliosphere's boundaries. Mars has been a focal point for exploration, with a rich history of robotic missions that have revealed the planet's geology, climate, and potential for life. NASA's Viking missions in the 1970s conducted the first experiments on Martian soil, searching for signs of microbial life. Decades later, rovers like Spirit, Opportunity, Curiosity, and Perseverance have traversed the planet's surface, uncovering evidence of ancient rivers, lakes, and potentially habitable environments. Perseverance, equipped with advanced instruments and accompanied by the Ingenuity helicopter, is currently collecting samples for future return to Earth. The exploration of Venus has provided insights into planetary evolution and climate. The Soviet Union's Venera program achieved the first successful landing on Venus, capturing images and data from its hellish surface. More recently, ESA's Venus Express and Japan's Akatsuki orbiter have studied the planet's thick atmosphere and dynamic weather, helping scientists understand the runaway greenhouse effect that transformed Venus into a scorching wasteland. The gas giants have also been targets of ambitious missions. NASA's Galileo spacecraft orbited Jupiter in the 1990s, studying its turbulent atmosphere, immense magnetic field, and diverse moons. Galileo revealed the potential for subsurface oceans on Europa, sparking interest in its habitability. Similarly, the Cassini-Huygens mission revolutionized our understanding of Saturn, its rings, and its moons. Cassini's long-term observations of the Saturnian system and Huygens' historic landing on Titan have provided unparalleled insights into these alien worlds. Asteroid and comet missions have expanded our knowledge of the solar system's building blocks. NASA's OSIRIS-RX recently collected samples from the near-Earth asteroid Bennu, while Japan's Hayabusa and Hayabusa 2 missions returned samples from asteroids Itokawa and Ryugu. These missions provide clues about the early solar system and the role of asteroids in delivering water and organic molecules to Earth. Meanwhile, ESA's Rosetta mission made history by orbiting and landing on Comet 67P/Churyumov-Gerasimenko, revealing its composition and activity in stunning detail. One of the most ambitious space missions to date is the James Webb Space Telescope (JWST), which launched in December 2021. Positioned at the Sun-Earth Lagrange Point 2, JWST is providing unprecedented views of the universe, from the earliest galaxies to the atmospheres of distant exoplanets. Its advanced infrared capabilities are transforming our understanding of planetary systems and the origins of stars and galaxies. Exploration has not been limited to the solar system. Spacecraft like New Horizons have ventured beyond, with its 2015 flyby of Pluto and subsequent exploration of Kuiper belt objects like Arrokoth offering insights into these distant, icy worlds. The Hubble Space Telescope, though primarily focused on the universe beyond the solar system, has also provided invaluable observations of planets, moons, and asteroids within our own cosmic neighborhood. Looking to the future, space agencies are planning missions to some of the most tantalizing destinations in the solar system. NASA's Europa Clipper will explore Europa's subsurface ocean, while ESA's JUICE, Jupiter Icy Moons Explorer, will study Ganymede, Callisto, and Europa in detail. The Dragonfly mission will send a drone-like rotorcraft to Titan, investigating its methane lakes and potential for life. Meanwhile, plans for missions to Uranus and Neptune aim to fill gaps in our knowledge of the ice giants. Human exploration is also entering a new era. NASA's Artemis program is set to return humans to the moon, with plans to establish a sustainable presence that could serve as a stepping stone for future missions to Mars. Private companies like SpaceX are developing technologies to support human exploration of the Red Planet, while international collaborations are advancing the possibilities of interplanetary travel. The challenges of space exploration are immense. Spacecraft must endure extreme temperatures, radiation, and the vast distances between celestial bodies. Communication delays, the need for autonomy, and the scarcity of resources on other worlds add to the complexity. Yet, each mission overcomes these challenges through innovation, perseverance, and international cooperation. The impact of space missions extends beyond scientific discoveries. They inspire humanity, fostering a sense of wonder and unity as we explore the unknown. They drive technological advancements, from miniaturized sensors to advanced propulsion systems that benefit life on Earth. Most importantly, they remind us of our shared curiosity and determination to push the boundaries of what is possible. Space missions are the embodiment of humanity's quest for knowledge and exploration. As we continue to probe the unknown, we unlock not only the secrets of the cosmos, but also the potential of our own ingenuity and resilience. The story of space exploration is far from over. It is an ever-evolving narrative that promises to expand our horizons and deepen our understanding of the universe. Future exploration, human ambitions in the solar system. The quest to explore the solar system has brought humanity to a pivotal moment, where dreams of interplanetary travel and colonization are transitioning from science fiction to tangible plans. The future of space exploration is brimming with ambitious goals, from establishing permanent habitats on the Moon and Mars to mining asteroids and venturing deeper into the icy realms of the outer solar system. What will it take to achieve these milestones? And how will these endeavors shape humanity's destiny in the cosmos? The Moon, our closest celestial neighbor, is poised to play a central role in the next era of space exploration. NASA's Artemis program, named after the twin sister of Apollo, aims to return humans to the lunar surface by the mid-2020s. Artemis I, the first uncrewed test mission, has already demonstrated the capabilities of the Space Launch System, SLS, and the Orion spacecraft. Subsequent missions will focus on landing astronauts near the Moon's south pole, where permanently shadowed craters hold vast reserves of water ice, a critical resource for sustaining life and producing fuel. Beyond short-term missions, Artemis envisions the creation of a sustainable lunar base, known as the Lunar Gateway. This orbiting station will serve as a hub for scientific research, technology testing, and preparation for deeper space missions. Private companies, such as SpaceX and Blue Origin, are collaborating with NASA to develop the technologies needed for these lunar endeavors, marking a new era of public-private partnerships in space exploration. Mars represents the next great frontier for human exploration. The Red Planet has long captured the imagination of scientists, engineers, and visionaries, not only for its potential habitability, but also for its parallels to Earth's past. The thin atmosphere, the presence of frozen water, and evidence of ancient rivers and lakes make Mars a compelling target for exploration and colonization. NASA's long-term goal is to send humans to Mars in the 2030s. The agency is developing advanced spacecraft, habitats, and life support systems to withstand the months-long journey and the harsh conditions of the Martian surface. Meanwhile, SpaceX's Starship, designed for interplanetary travel, aims to transport large crews and cargo to Mars, with the ultimate vision of establishing a self-sustaining Martian city. Such a settlement could ensure humanity's survival in the event of a global catastrophe on Earth, marking the beginning of a multi-planetary civilization. Challenges abound in making Mars colonization a reality. The thin atmosphere offers little protection from cosmic radiation, and the lack of a magnetic field exposes the surface to solar winds. Engineering solutions, such as underground habitats or radiation-shielded domes, are being explored to address these risks. Developing closed-loop life support systems, growing food in Martian soil, and producing fuel and oxygen from local resources are critical steps towards sustainable living on Mars. Asteroid mining is another burgeoning area of interest that could revolutionize space exploration and industry. Near-Earth asteroids are rich in valuable materials, including metals like platinum, nickel, and iron, as well as water ice. Companies like Planetary Resources and Deep Space Industries are pioneering technologies to harvest these resources, which could support space-based manufacturing, reduce the costs of space exploration, and even supply materials for Earth's industries. The concept of in situ resource utilization, ISRU, using local materials to support missions, extends to the Moon, Mars, and beyond. Lunar regolith can be processed into building materials, while water ice on the Moon and Mars can be split into hydrogen and oxygen for fuel and life support. These capabilities are essential for creating self-sufficient colonies and reducing dependence on Earth. Looking farther afield, the outer solar system holds untapped potential for exploration. Moons like Europa, Enceladus, and Titan are prime targets in the search for extraterrestrial life. Europa Kuiper and Dragonfly missions will investigate these icy worlds, probing their subsurface oceans and organic-rich environments. While human missions to the outer planets remain a distant goal, robotic explorers and advanced propulsion technologies could pave the way for future manned missions. Advances in propulsion systems are critical for achieving these ambitions. Traditional chemical rockets, while reliable, are inefficient for interplanetary travel. Concepts such as nuclear thermal propulsion, ion engines, and solar sails promise faster and more cost-effective journeys to distant destinations. Breakthroughs in these technologies could dramatically expand the scope of human and robotic exploration. International collaboration will also play a pivotal role in the future of space exploration. The International Space Station, ISS, has demonstrated the power of global partnerships, bringing together nations to conduct scientific research and foster cooperation. Future projects, such as the Lunar Gateway and Mars missions, are likely to involve contributions from multiple countries, combining expertise, resources, and innovation to achieve shared goals. As humanity pushes deeper into the solar system, ethical and philosophical questions arise. How do we balance exploration with the preservation of extraterrestrial environments? Should humanity have the right to exploit the resources of other worlds, or should these be regarded as part of a shared cosmic heritage? These debates are gaining urgency as the pace of exploration accelerates. The future of space exploration is not just about technological achievements. It is about redefining what it means to be human. Venturing beyond Earth challenges us to innovate, collaborate, and adapt. It inspires us to look beyond our differences and focus on the shared goal of understanding our place in the universe. As we stand on the brink of this new era, the possibilities are as boundless as the cosmos itself. The Moon, Mars, and the farthest reaches of the solar system are no longer distant dreams, but achievable realities. Each mission brings us closer to answering fundamental questions about life, the origins of the universe, and the future of humanity. In the words of Carl Sagan, exploration is in our nature. We began as wanderers, and we are wanderers still. The solar system's legacy, reflections on exploration and discovery. As we journey through the solar system, from the sun's fiery heart to the icy realms of the Kuiper belt and the Oort cloud, we are reminded of the intricate beauty and boundless complexity of our cosmic neighborhood. The solar system is more than a collection of celestial bodies. It is a narrative of creation, destruction, and renewal, a story billions of years in the making. But as we stand on the threshold of deeper exploration, what lessons can we draw from our discoveries? How does the legacy of the solar system shape our understanding of the universe and our place within it? The solar system's formation, born from the chaotic collapse of a molecular cloud, is a testament to the power of gravity, time, and chance. The sun, planets, moons, and smaller bodies are all products of this transformative process, each a unique piece of a cosmic puzzle. The rocky worlds of the inner solar system reveal the scars of their violent pasts, from volcanic upheavals to asteroid impacts. The gas giants, with their swirling storms and intricate ring systems, showcase the power of planetary migration and gravitational interplay. Meanwhile, The icy worlds of the outer solar system hold the keys to understanding the primordial materials that shaped our sun and planets. One of the most profound revelations of solar system exploration is its diversity. No two worlds are alike. Mercury's barren, cratered surface contrasts sharply with the volcanic activity of Venus. Earth, teeming with life, stands in stark opposition to the arid deserts of Mars. The gas and ice giants each boast unique characteristics, from Jupiter's raging storms to Uranus's tilted axis and Neptune's supersonic winds. Even among the moons, we find a staggering variety, from Europa's icy crust hiding a potential ocean to Titan's methane lakes and Enceladus's geysers of water vapor. This diversity challenges our understanding of planetary science, forcing us to question long-held assumptions about how planets and moons form and evolve. It also expands our search for life, pushing the boundaries of habitability. Could microbes thrive in the hydrothermal vents of Europa's ocean or the icy plumes of Enceladus? Could life have once emerged on Mars during its wetter, more temperate past? These questions drive not only exploration, but also our understanding of life's potential across the cosmos. The solar system is also a laboratory for studying the effects of time. Over billions of years, gravitational interactions have shaped the orbits of planets and smaller bodies, while impacts, erosion, and tectonic activity have sculpted their surfaces. By examining these processes, we gain insights into the forces that have shaped Earth's own evolution. The asteroid belt and Kuiper belt, rich with ancient debris, serve as time capsules preserving the conditions of the early solar system, while comets provide glimpses of the materials that may have seeded life on Earth. As we look outward, the solar system serves as a bridge to the universe beyond. The discovery of exoplanets has revealed that planetary systems come in an astonishing array of configurations, many of which differ significantly from our own. Yet, by studying the solar system, we develop tools and models to understand these distant worlds, comparing their atmospheres, compositions, and orbits to the planets and moons we know. The legacy of solar system exploration is also a story of human ingenuity and perseverance. From the earliest telescopic observations to the groundbreaking missions of Voyager, Cassini, New Horizons, and Perseverance, each step has expanded the boundaries of what is possible. These achievements reflect the collaborative efforts of scientists, engineers, and explorers across generations and borders, united by a shared curiosity about the universe. As humanity prepares for the next chapter of exploration, the solar system remains both a frontier and a home. The Moon and Mars, once distant aspirations, are now destinations for human settlement, offering opportunities to test our resilience and adaptability. Asteroids and icy moons present resources that could support future missions, while the outer planets beckon with their mysteries, challenging us to venture farther. Yet the solar system's legacy is not only about discovery, it is also about responsibility. As we explore and utilize its resources, we must consider the ethical implications of our actions. How do we balance exploration with preservation? How do we ensure that the solar system remains a place of shared wonder for future generations? These questions remind us that the solar system is not just a destination, but a heritage, a part of the universe that we are privileged to call home. The solar system's story is far from over. As we continue to probe its depths and expand our horizons, we are reminded of its infinite capacity to surprise, inspire, and teach. It is a reminder of the interconnectedness of all things, from the smallest comet to the largest gas giant, and of our place within this grand cosmic tapestry. In exploring the solar system, we explore ourselves, our curiosity, our ingenuity, and our capacity to dream. It is a journey not just through space, but through time, a voyage that connects us to the past, the present, and the future. As we look to the stars, the solar system remains our guide, a beacon of possibility in the vastness of the cosmos. The boundaries of the solar system, venturing beyond. The solar system's boundaries are not clearly defined, but they mark the transition from the sun's influence to the interstellar environment of the Milky Way. Beyond the known planets, moons, and smaller bodies lies a frontier of science and imagination, where the sun's gravity gives way to the forces of the galaxy. What lies beyond the solar system? How do we define its edge, and what challenges await as we aim to explore these distant regions? The most immediate boundary of the solar system is the heliosphere, a bubble of charged particles and magnetic fields created by the solar wind. Extending well beyond Pluto, the heliosphere serves as a protective shield, deflecting cosmic rays and interstellar material. Voyager 1 and Voyager 2, launched in 1977, have provided humanity's first direct observations of the heliosphere's boundary, the heliopause, where the solar wind's influence wanes and interstellar space begins. These spacecraft revealed a dynamic interaction between the sun's influence and the surrounding galactic medium, offering a glimpse into the complex environment at the edge of the solar system. Beyond the heliosphere lies the Oort cloud, a hypothetical region populated by trillions of icy bodies. Thought to be the source of long-period comets, the Oort cloud extends up to 100,000 astronomical units, AU, from the Sun, enveloping the solar system in a vast, spherical shell. While no direct observations of the Oort cloud have been made, its existence is inferred from the behavior of comets that occasionally enter the inner solar system. Exploring the Oort cloud remains a distant dream, as its immense size and faint objects pose significant challenges for observation and study. The interstellar medium, the matter and radiation that fill the space between stars, lies beyond the Oort cloud. Composed primarily of hydrogen and helium, along with traces of heavier elements and cosmic dust, the interstellar medium is a key component of the Milky Way's ecosystem. It is both a remnant of past stellar activity and the raw material for future star formation. Studying the interstellar medium is critical for understanding the galaxy's evolution and the environment that surrounds the solar system. Interstellar exploration represents the ultimate challenge for space exploration. The vast distances involved make it difficult to design missions capable of reaching even the nearest stars within a human lifetime. Proxima Centauri, the closest star system, lies over 4 light-years away, a distance of approximately 40 trillion kilometers, 25 trillion miles. At current spacecraft speeds, it would take tens of thousands of years to reach such a destination. However, advancements in propulsion technology, such as light sails, nuclear propulsion, and antimatter engines, may one day make interstellar travel feasible. One of the most promising interstellar exploration concepts is Breakthrough Starshot, an initiative to send tiny, light-powered probes to Alpha Centauri. These probes, propelled by powerful lasers, could travel at a fraction of the speed of light, reaching the star system in just a few decades. While still in its conceptual phase, Breakthrough Starshot represents a bold step toward interstellar exploration, offering a glimpse of what might be possible with innovative technologies and international collaboration. As humanity contemplates venturing beyond the solar system, ethical and philosophical questions arise. What responsibilities do we have toward potential extraterrestrial ecosystems? How do we ensure that our exploration does not harm the environments we encounter? These questions underscore the need for careful planning and a commitment to preserving the integrity of the cosmos. The boundaries of the solar system are not just physical. They are conceptual, representing the limits of human knowledge and the potential for discovery. By pushing these boundaries, we expand our understanding of the universe and our place within it. The journey beyond the solar system is not just a technological challenge. It is a testament to humanity's enduring curiosity and determination to explore the unknown. The solar system's edge is not an endpoint but a gateway, a portal to the stars and the infinite possibilities that lie beyond. As we stand on the threshold of interstellar exploration, we are reminded that the universe is vast, and our journey has only just begun. The search for extraterrestrial life. Are we alone? One of the most profound questions humanity has ever asked is, are we alone in the universe? The solar system, with its diverse worlds and dynamic environments, offers tantalizing hints that life may exist beyond Earth. From the possibility of microbial life in subsurface oceans to the search for biosignatures in exoplanets' atmospheres, the quest to find extraterrestrial life is driving some of the most ambitious scientific efforts of our time. But where should we look? And what would finding life mean for our understanding of the cosmos? Life beyond Earth, promising candidates in the solar system. Within the solar system, several worlds stand out as potential habitats for life. These are places where water, energy, and the right chemical ingredients may combine to create conditions conducive to biology. Mars, with its history of liquid water, remains a prime target. Evidence of ancient riverbeds, lakes, and possibly an ocean suggests that Mars was once warmer and wetter. NASA's Perseverance rover is actively exploring the Jezero crater, an ancient lakebed, searching for signs of past life and collecting samples for future return to Earth. Underground aquifers or subsurface ice might still harbor microbial life, protected from the harsh surface conditions. Europa, a moon of Jupiter, has captivated scientists with its potential for a subsurface ocean beneath a thick, icy crust. Tidal heating, caused by gravitational interactions with Jupiter, keeps this ocean liquid, creating a possible habitat for life. The upcoming Europa Clipper mission will investigate the moon's ice shell and subsurface ocean, seeking clues about its chemistry and habitability. Enceladus, a small moon of Saturn, has shown extraordinary promise as well. Geysers at its south pole eject plumes of water vapor, ice particles, and organic compounds into space. These plumes are believed to originate from a subsurface ocean, making Enceladus a prime candidate for life. Future missions could sample these plumes directly, searching for molecular signatures of living organisms. Titan, Saturn's largest moon, presents a unique environment with lakes and seas of liquid methane and ethane. While vastly different from Earth, Titan's complex organic chemistry could support exotic forms of life. NASA's Dragonfly mission, set to launch in the 2030s, will explore Titan's surface, investigating its potential for both prebiotic chemistry and life. Beyond these well-known candidates, other moons, and even asteroids may harbor niches for life. Ceres, the largest object in the asteroid belt, has shown evidence of water vapor and possible briny reservoirs beneath its surface. Venus, once considered inhospitable, sparked interest in 2020 with the potential detection of phosphine in its clouds, a gas that, on Earth, is associated with biological processes. Although controversial, this discovery has reignited the search for microbial life in Venus's temperate upper atmosphere. The search for biosignatures. Identifying life requires recognizing its biosignatures, or evidence of biological activity. On Earth, these include specific combinations of gases, such as oxygen and methane, that indicate life's presence. In the solar system, biosignatures could take the form of organic molecules, isotopic ratios, or even the chemical composition of atmospheres. For worlds like Europa and Enceladus, biosignatures might be found in the plumes of water or in the chemistry of their oceans. On Mars, ancient biosignatures might be preserved in rocks or soil, while modern life might release trace gases like methane into the thin atmosphere. Titan's complex organic molecules could offer hints of an alternative form of life based on hydrocarbons instead of water. Beyond the solar system, the search for biosignatures extends to exoplanets. The James Webb Space Telescope, JWST, is equipped to analyze the atmospheres of distant planets, detecting molecules like water vapor, carbon dioxide, methane, and ozone. The discovery of such gases in the right combinations could point to biological processes. Future missions, such as the European Space Agency's Ariel and NASA's proposed LUVOIR Observatory, aim to survey the atmospheres of hundreds of exoplanets, bringing us closer to identifying potentially habitable worlds. Technosignatures and the search for intelligent life. The search for life is not limited to microbes. Efforts to detect intelligent civilizations have focused on technosignatures, evidence of advanced technology. These include radio signals, artificial light, megastructures like Dyson spheres, or even pollution in exoplanet atmospheres. The search for extraterrestrial intelligence, SETI, has been at the forefront of this effort, scanning the skies for radio signals that could indicate the presence of advanced civilizations. Recent advances in data processing and machine learning have enhanced SETI's capabilities, enabling it to analyze vast amounts of data more efficiently. Another approach involves looking for anomalies that natural processes cannot explain. For instance, unusual patterns of starlight dimming, as initially observed with Tabby's star, have sparked discussions about potential artificial structures. While such observations often have natural explanations, They remind us of the need to remain open to unexpected discoveries. What finding life would mean? Discovering extraterrestrial life, whether microbial or intelligent, would be one of the most transformative events in human history. It would fundamentally alter our understanding of biology, evolution, and the uniqueness of life on Earth. A second genesis, life arising independently elsewhere, would confirm that life is not a cosmic rarity, but a common consequence of the universe's processes. The implications for humanity's philosophical and spiritual frameworks would be profound. Questions about our place in the universe, the nature of intelligence, and the potential for communication with other civilizations would dominate scientific and cultural discourse. Would we see ourselves as part of a larger cosmic community or as guardians of a fragile oasis of life? The challenges ahead. The search for extraterrestrial life is not without its challenges. Detecting faint biosignatures from distant worlds requires extraordinary precision, and distinguishing biological processes from abiotic ones is complex. Missions to the outer solar system and beyond must overcome technical hurdles, from extreme distances to harsh environments. Yet, each step forward brings us closer to answering the ultimate question of whether we are alone. The legacy of the search. The search for life is as much about exploration as it is about discovery. It embodies humanity's deepest curiosity and our desire to connect with the universe. Whether life is found on a distant moon, in the atmosphere of a faraway planet, or not at all, the pursuit will deepen our understanding of what it means to be alive and of our place in the grand tapestry of existence. As we peer into the cosmos, the search for life reminds us of the interconnectedness of all things and the profound mysteries that still await. The journey continues, fueled by the hope that somewhere, amid the stars and the planets, life, perhaps vastly different from our own, may be reaching out, waiting to be found. The solar system and the Milky Way, a galactic perspective. The solar system is not an isolated entity. It is an integral part of the Milky Way galaxy, a vast cosmic structure containing hundreds of billions of stars, planets, and an array of celestial phenomena. By understanding the solar system's relationship with the Milky Way, we gain a broader perspective on its formation, evolution, and ultimate fate. How does our solar system fit into this galactic context, and what role does the Milky Way play in shaping its destiny? The solar system's location in the galaxy. The solar system resides in one of the Milky Way's spiral arms, the Orion Arm, a relatively quiet region of space situated about 27,000 light-years from the galactic center. This location is significant. It lies within the galaxy's habitable zone, often called the galactic Goldilocks zone. This region is far enough from the galactic core to avoid the intense radiation and gravitational disruptions caused by the supermassive black hole at the center, yet close enough to have access to the elements necessary for planet and star formation. The Milky Way is a barred spiral galaxy with a dense central bulge, a bar-shaped cluster of stars, and 4 prominent spiral arms extending outward. The galaxy's disk is surrounded by a vast halo of dark matter and old stars, while its core contains a supermassive black hole, known as Sagittarius A*, which influences the dynamics of the entire galaxy. The influence of the galaxy on the solar system. The Milky Way's structure and dynamics have played a critical role in shaping the solar system's evolution. The galaxy's gravitational forces influenced the collapse of the molecular cloud that gave birth to the Sun and planets. Over billions of years, the solar system has orbited the galactic center, completing one revolution approximately every 225 to 250 million years, a period known as a galactic year. This journey is not a smooth ride. The solar system passes through regions of varying density and activity, including spiral arms rich in star-forming material. These encounters may increase the likelihood of gravitational perturbations, which can dislodge comets from the Oort cloud and send them hurtling toward the inner solar system. Such events may have contributed to periods of intense bombardment, like the Late Heavy Bombardment, which reshaped the surfaces of the Moon, Mars, and Earth. The solar system's galactic neighborhood. Our solar system exists within a broader galactic neighborhood, surrounded by nearby stars, stellar remnants, and interstellar clouds. The closest star system, Alpha Centauri, lies just over 4 light-years away and includes Proxima Centauri, a red dwarf with a potentially habitable exoplanet, Proxima b. Other notable neighbors include Barnard Star, Sirius, and the recently discovered interstellar objects like Oumuamua and Comet 2I/Borisov, which provide glimpses into the materials from other star systems. The solar system is also part of the local bubble, a cavity in the interstellar medium thought to have been carved out by ancient supernovae. This region is relatively sparse, with low-density gas and dust, creating a unique environment for the solar system's journey through the galaxy. The Milky Way's evolution and its impact. The Milky Way itself is a dynamic and evolving entity. Over billions of years, it has undergone mergers with smaller galaxies, absorbing their stars, gas, and dark matter. Evidence of these events can be seen in the streams of stars that orbit the galactic halo, remnants of past mergers. The galaxy is currently interacting with the Large Magellanic Cloud and Small Magellanic Cloud, two satellite galaxies, and is on a collision course with the Andromeda Galaxy, its largest neighbor. The eventual merger with Andromeda, expected in about 4.5 billion years, will dramatically reshape both galaxies. While individual stars and planetary systems are unlikely to collide, the gravitational interactions will distort their orbits, potentially ejecting some systems into intergalactic space or drawing them closer to the new galactic center. The role of the Milky Way in planetary and stellar formation. The Milky Way's vast resources of gas and dust make it a fertile environment for the formation of stars and planets. Star-forming regions, such as the Orion Nebula and the Carina Nebula, are stellar nurseries where massive clouds collapse to create new stars and planetary systems. The distribution of elements, particularly heavy elements like carbon, oxygen, and iron, plays a critical role in determining the types of planets that can form. These elements were forged in the cores of earlier generations of stars and distributed by supernovae, enriching the interstellar medium. The solar system's future in the galactic context. As the solar system continues its journey through the Milky Way, its ultimate fate will be shaped by both internal and external forces. The Sun, currently a stable main-sequence star, will exhaust its hydrogen fuel in about 5 billion years, expanding into a red giant and engulfing the inner planets, including Earth. The outer planets and the remnants of the solar system may survive this transformation, orbiting the Sun's final stage, a dense white dwarf. On a larger scale, the Milky Way's collision with Andromeda will redefine the solar system's place in the galaxy. The resulting structure, often referred to as Milkomeda, will merge the two galaxies into a single elliptical or lenticular galaxy. The solar system may find itself in a new orbit, potentially far from the galactic core, in a vastly changed environment. Galactic exploration, the next frontier. As humanity advances its understanding of the Milky Way, the possibilities for exploration expand. Missions to study interstellar space, such as Voyager and Future probes, provide a glimpse of the galaxy beyond the solar system. The search for exoplanets, particularly those in the galactic habitable zone, may reveal worlds that share characteristics with Earth, offering new targets for exploration and the search for life. The Milky Way, with its billions of stars and countless planetary systems, is a microcosm of the universe's complexity. By studying our galaxy, we gain insights into the processes that shape stars, planets, and life itself. As we continue to explore the solar system and the broader galaxy, we are reminded of our shared connection to the cosmos, a connection that inspires us to reach farther and dream bigger. The solar system's ultimate fate, a glimpse into the far future. As vast and dynamic as the solar system is, its existence is not eternal. Over billions of years, the Sun and its planetary family will undergo dramatic changes, shaped by the relentless forces of stellar evolution and the gravitational dance of the galaxy. What will happen to the Sun, Earth, and the other planets in the distant future? How does the solar system's fate connect to the broader evolution of the universe? The Sun's stellar evolution. The Sun, like all stars, is finite in its lifespan. Currently a middle-aged star in its stable main-sequence phase, the Sun has been converting hydrogen into helium through nuclear fusion for approximately 4.6 billion years. This process generates the energy that powers the Sun and sustains life on Earth. However, the Sun's hydrogen fuel is not limitless. In about 5 billion years, the Sun will exhaust the hydrogen in its core, marking the end of its main sequence phase. Without the outward pressure of fusion to counteract gravity, the core will contract and heat up, igniting the fusion of helium into heavier elements like carbon and oxygen. During this phase, the Sun will expand into a red giant, engulfing the inner planets, including Mercury and Venus. Earth's fate remains uncertain. While it may avoid being swallowed, the intense heat and radiation will render it uninhabitable, boiling away its oceans and atmosphere. The end of the solar system as we know it. As the Sun sheds its outer layers during the red giant phase, it will create a beautiful planetary nebula, a glowing shell of ionized gas surrounding the remnants of the star. The Sun's core will eventually stabilize as a white dwarf, a dense, Earth-sized remnant composed primarily of carbon and oxygen. This white dwarf will no longer produce energy through fusion, but will glow faintly for billions of years as it gradually cools. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are expected to survive the Sun's transformation, although their orbits may change due to the loss of the Sun's mass. The icy bodies of the Kuiper belt and Oort cloud will remain, but their interactions with the galaxy may eventually scatter them, leaving only a sparse remnant of the solar system. The role of galactic forces. The solar system's fate is not solely determined by the Sun. Over billions of years, the gravitational influence of passing stars and the Milky Way's galactic tides will perturb the orbits of the solar system's outer objects. Some Oort cloud comets may be ejected into interstellar space, while others could be sent plunging toward the inner solar system as comets. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy. This event will dramatically reshape both galaxies, creating a new structure often referred to as Milkomeda. While the solar system is unlikely to collide with another star during this merger, its orbit within the galaxy will change, potentially flinging it to the outskirts of the newly formed galaxy or closer to its core. The long-term future of the solar system. As the universe continues to evolve, the solar system will face additional changes. 1. White dwarf cooling. The Sun's white dwarf will cool and dim over trillions of years, eventually becoming a cold, dark black dwarf. By this point, the solar system will be unrecognizable, with only cold, inert remnants remaining. 2. Planetary orbits. Over extremely long timescales, the gravitational interactions of the outer planets may destabilize their orbits, leading to collisions or ejections from the solar system. Rogue planets may drift into interstellar space, separated from their parent star. 3. Galactic and universal evolution. The Milky Way-Andromeda merger will mark a major transformation in the galaxy's structure, but the universe's expansion will continue. Over tens of trillions of years, the stars of the galaxy will burn out, leaving behind a dark era dominated by black holes, neutron stars, and cold white dwarfs. The end of the universe and its implications. The solar system's ultimate fate is tied to the broader fate of the universe itself, which depends on its fundamental properties. 1. The Big Freeze. If the universe's expansion continues indefinitely, galaxies will drift apart, and star formation will cease as interstellar gas is depleted. Over unimaginably long timescales, black holes will dominate, eventually evaporating through Hawking radiation. 2. The Big Crunch. If the universe's expansion slows and reverses, it may collapse in a big crunch, potentially leading to a new cycle of cosmic rebirth. 3. The Big Rip. In a universe dominated by dark energy, the accelerated expansion could eventually tear apart galaxies, stars, and even atoms, ending the universe in a big rip. While these scenarios lie far beyond human timescales, they provide a framework for understanding the solar system's place in the grand cosmic narrative. Reflections on the solar system's legacy. The solar system's journey from its chaotic birth to its ultimate dissolution is a testament to the dynamism of the universe. It has been a cradle of life, a source of wonder, and a catalyst for humanity's exploration of the cosmos. As we contemplate its future, we are reminded of the impermanence of all things and the interconnectedness of the universe's cycles of creation and destruction. Our exploration of the solar system has only just begun. Each mission, each discovery, brings us closer to understanding not only its origins and destiny, but also the processes that govern the universe. The solar system's legacy is one of resilience, transformation, and the enduring mystery of existence. Cosmic impacts, shaping the solar system and life on Earth. Throughout the history of the solar system, collisions between celestial bodies have been a defining force. From the violent impacts that formed the planets to the asteroid strikes that shaped the evolution of life on Earth, these cosmic collisions are both destructive and transformative. What role have impacts played in the solar system's past, and what risks do they pose for the future? Can we defend our planet from catastrophic collisions? The role of impacts in solar system formation. Impacts were fundamental to the solar system's creation. In the chaotic early solar system, planetesimals, the building blocks of planets, collided and merged, forming the protoplanets that would eventually become the planets we know today. The largest of these impacts reshaped worlds on a colossal scale. For example, the Moon is thought to have formed after a giant impact between the young Earth and a Mars-sized protoplanet called Theia. The debris from this collision coalesced into the Moon, giving Earth its stable tilt and tides. Mercury's high density and thin crust suggest it may have lost much of its outer layers in a massive collision early in its history. Uranus's extreme axial tilt is likely the result of a colossal impact with another celestial body, which tipped the planet on its side. Impacts also played a role in delivering essential ingredients for life. Comets and asteroids bombarded the inner planets during the late heavy bombardment, approximately 4 billion years ago, bringing water and organic molecules to Earth. These collisions may have seeded the early Earth with the materials necessary for life to emerge. Impacts and life on Earth. While impacts can create life-friendly conditions, they can also cause mass extinctions. Earth's geological record contains evidence of several major impact events, including the Chicxulub impact, 66 million years ago, which led to the extinction of the dinosaurs and 75% of all species on Earth. This event created a 150-kilometer-wide crater in present-day Mexico and released an immense amount of energy, causing wildfires, tsunamis, and a nuclear winter effect that disrupted the climate. The Tunguska event of 1908, a smaller but still significant impact, flattened 2,000 square kilometers of Siberian forest. Believed to have been caused by an exploding meteoroid, it highlighted the destructive potential of smaller objects. Despite their destructive power, impacts can also create opportunities for life to adapt and thrive. The extinction of the dinosaurs, for example, allowed mammals to diversify and eventually led to the rise of humans. Impact threats today. The risk of impacts persists. Near-Earth objects, NEOs, asteroids and comets that come within 1.3 astronomical units of Earth, pose the greatest threat. While large impacts are rare, even smaller objects can cause significant damage. Recent examples include the Chelyabinsk meteor in 2013, which exploded over Russia, injuring over 1,500 people and causing widespread property damage. The meteoroid was only 20 meters in diameter, but released the energy equivalent of 500 kilotons of TNT. Tracking and defending against impacts. To mitigate the threat of impacts, scientists and space agencies around the world are working to identify and track NEOs. NASA's Planetary Defense Coordination Office and similar programs globally use telescopes and radar to map the trajectories of potentially hazardous objects. As of now, no large object is on a collision course with Earth in the near future, but continued monitoring is essential. Technological advances are making planetary defense a reality. In 2022, NASA conducted the Double Asteroid Redirection Test, DART, the first mission designed to deflect an asteroid by deliberately crashing a spacecraft into it. The mission targeted the small asteroid, Moonlet Dimorphos, and successfully altered its orbit, demonstrating that humanity can intervene to prevent potential impacts. Proposed methods for deflecting asteroids include kinetic impactors, using spacecraft to physically nudge an asteroid off its trajectory; gravity tractors, positioning a spacecraft near an asteroid to gradually alter its path using gravitational attraction; laser ablation, using lasers to heat the surface of an asteroid, causing material to vaporize and create thrust; nuclear explosions, deploying nuclear devices to either fragment or redirect an asteroid, though this method is controversial due to potential risks. The broader impact of collisions. Beyond their immediate effects, impacts have shaped the solar system's evolution. Craters on the Moon, Mars, and Mercury provide a record of ancient collisions, helping scientists understand the history of planetary surfaces. These craters are not just scars. They offer clues about the frequency and intensity of impacts throughout the solar system's history. Asteroid impacts also inspire technological innovation and international cooperation. Programs to detect and prevent collisions unite nations in a shared effort to protect the planet. They also drive advancements in space exploration, such as asteroid mining, which could turn potential threats into valuable resources. Living with the risks. While the probability of a catastrophic impact is low, the consequences could be devastating. Continued investment in planetary defense is crucial for safeguarding humanity's future. Public education and international collaboration are also essential to ensure that we are prepared to respond effectively to potential threats. Reflections on cosmic impacts. Cosmic collisions are a reminder of the solar system's dynamism and the interconnectedness of its celestial bodies. They highlight both the fragility and resilience of life, showing how destruction can lead to renewal. As we learn to mitigate these risks, we are also gaining a deeper appreciation of the forces that have shaped our world and the cosmos. Impacts are not just a threat. They are part of the solar system's story, a story of creation, transformation, and survival. By studying and preparing for these events, we embrace our role as stewards of Earth and explorers of the universe, ready to face the challenges of an ever-changing cosmos. The cosmic dance. Gravitational forces in the solar system. Gravitational forces are the invisible threads that weave the solar system into a cohesive and dynamic structure. They dictate the movements of planets, moons, asteroids, and comets, orchestrating a celestial dance that has unfolded over billions of years. From the stability of planetary orbits to the chaotic trajectories of distant objects, gravity governs every interaction within the solar system. But how does this fundamental force shape the solar system's past, present, and future? The role of gravity in planetary formation. Gravity was the architect of the solar system. During its formation, gravity pulled together gas and dust from a collapsing molecular cloud, creating the Sun at the center. The remaining material flattened into a spinning protoplanetary disk, where gravity clumped particles into planetesimals, the seeds of planets. Over time, these planetesimals grew through collisions and accretion, forming the protoplanets that would become the planets we know today. Even after the planets formed, gravity continued to shape their orbits and interactions. The migration of the giant planets, particularly Jupiter and Saturn, influenced the distribution of smaller bodies, sculpting regions like the asteroid belt, Kuiper belt, and Oort cloud. These gravitational interactions also determined the spacing and stability of the planets' orbits, preventing collisions and ensuring the long-term stability of the solar system. Orbital mechanics, the cosmic ballet. The predictable movements of celestial bodies are governed by the laws of orbital mechanics, first described by Johannes Kepler and later refined by Isaac Newton and Albert Einstein. Planets follow elliptical orbits around the Sun, with their speed and distance from the Sun dictated by its immense gravitational pull. This balance between the Sun's gravity and the planet's inertia keeps them in their respective orbits. Moons, too, are bound by gravity, orbiting their parent planets in intricate patterns. Some moons, like Earth's moon, are tidally locked, always showing the same face to their planet due to gravitational interactions. Others, like Jupiter's Galilean moons, influence each other through resonances, where their orbital periods are linked in precise ratios. These resonances create complex gravitational relationships that shape the moon's geological activity and surface features. Gravity also governs the behavior of smaller bodies, such as asteroids and comets. The Trojan asteroids, for example, are trapped in stable regions of Jupiter's orbit known as Lagrange points, where the gravitational forces of the Sun and Jupiter balance. Similarly, comets from the Kuiper belt and Oort cloud are nudged into the inner solar system by gravitational perturbations, creating the spectacular displays we see in the night sky. Gravitational slingshots and space exploration. Gravity is not only a force of nature, but also a tool for exploration. Space missions frequently use gravitational slingshots to accelerate spacecraft and change their trajectories. By flying close to a planet or moon, a spacecraft can harness the planet's gravity to gain speed or alter its path without expending additional fuel. This technique has enabled some of the most ambitious missions in history. The Voyager spacecraft, for example, used gravitational assists from Jupiter and Saturn to journey to the outer solar system and beyond. Similarly, NASA's Cassini spacecraft used multiple slingshots around Venus, Earth, and Jupiter to reach Saturn, where it spent over a decade studying the planet, its rings, and its moons. Gravitational slingshots are also critical for missions to explore the Kuiper belt and interstellar space. By carefully planning these maneuvers, engineers can extend the range and capabilities of spacecraft, opening new frontiers for exploration. Tidal forces, gravity's subtle influence. Tidal forces, caused by differences in gravitational pull across a celestial body, create powerful effects on planets and moons. Earth's tides, driven by the gravitational pull of the moon and the sun, are a familiar example. These tides not only shape Earth's oceans but also influence its rotation, gradually slowing the planet's spin. In the solar system, tidal forces drive dramatic geological activity. Io, a moon of Jupiter, experiences intense tidal heating due to its elliptical orbit and gravitational interactions with Jupiter and neighboring moons. This heating powers Io's hundreds of active volcanoes, making it the most geologically active body in the solar system. Tidal forces also maintain subsurface oceans on moons like Europa, Enceladus, and possibly Titan, providing potential habitats for life. These interactions highlight the role of gravity in sustaining environments that might otherwise be lifeless. Chaotic orbits, the limits of predictability. While gravity provides stability, it can also lead to chaos. Over long timescales, gravitational interactions between planets and smaller bodies can create unpredictable changes in their orbits. This phenomenon, known as chaotic dynamics, has implications for the long-term evolution of the solar system. For example, small perturbations in the asteroid belt can send asteroids into Earth-crossing orbits, creating potential impact hazards. Similarly, the orbits of distant objects in the Kuiper belt and Oort cloud are influenced by passing stars and the galactic tide, occasionally sending comets into the inner solar system. Despite these chaotic elements, the overall structure of the solar system remains stable on human timescales. This balance between order and chaos is a hallmark of gravitational systems, demonstrating the interplay of predictable laws and dynamic interactions. Gravity beyond the solar system. The gravitational forces that govern the solar system are part of a larger cosmic framework. The solar system orbits the center of the Milky Way, completing one revolution every 225 to 250 million years. Within the galaxy, gravity binds stars into clusters, shapes the spiral arms, and dictates the orbits of stellar remnants and black holes. On an even grander scale, gravity drives the formation and evolution of galaxy clusters, filaments, and voids, shaping the large-scale structure of the universe. Einstein's theory of general relativity has shown that gravity is not just a force, but a curvature of space-time, influencing the motion of all matter and energy. Reflections on gravity's role. Gravity is the silent architect of the cosmos, shaping everything from the smallest moons to the largest galaxies. It creates order out of chaos, balances stability with dynamism, and governs the interactions that define the solar system. Without gravity, there would be no planets, no stars, and no life. Understanding gravity not only deepens our appreciation of the universe, but also empowers us to explore it. From predicting planetary motions to navigating spacecraft, gravity is both a mystery and a tool, a force that unites the cosmos and guides humanity's journey through it. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.